All right, good morning, everyone. Thank you for joining us this morning. My name is Amy Barad, and I'm the Director of Commercial Programs at the Massachusetts Clean Energy Center. On behalf of myself and Lauren Madison of UMass's Center for Energy Efficiency and Renewable Energy, I would like to welcome you to this training this morning. MassCEC and UMass designed this training to familiarize you with heat pump technology in general and VRF systems in particular, because we believe that this technology is an important means of helping us electrify commercial and multifamily housing, and thereby helping us achieve our greenhouse gas reduction goals. J.S. Rancourt of DXS Engineering and Greg Hasselbarth of Mitsubishi Electric put together most of the content of this program, and we'll be delivering it. They are both experienced VRF designers and have a deep understanding of this technology. Also speaking in addition are Kyle Kumis of Energy Solution, explaining some of the incentives that are available for these systems, and I will chime in on that subject as well. And just for organization purposes, for the whole presentation, we'd like to thank Lauren Madison. Our format's going to be tag team. Greg and JS will give more introductions about themselves when they first come up to speak. We'll take questions as we go, as time permits. We also plan to leave a little time for Q&A before our midway break and again at the end. So here is Greg Hasselbarth.
Thank you. Good morning. JS and I are just going to introduce ourselves before we start the presentation because we're going to be jumping back and forth, kind of sharing the presentation in different slides. My name is Greg Hasselbarth. I'm the Director of Commercial Business for the Northeast of Mitsubishi Electric. So for our Northeast territory, which is mostly New England, we're based right down the street in Southborough, Massachusetts, where we have our training center. We do a lot of contractor training, as well as our offices with service, marketing, engineering, sales. My role here is I've been focusing on VRF and VRF technology for the past 8 years with Mitsubishi. I work with a team of sales engineers, and our primary goal is to work with consultant engineers, architects, building owners, mechanical contractors, really anyone on the proper design and application of VRF equipment. So everything from conceptually looking at a building to see if it's a technology that fits, answering questions along the way to make sure that it's applied properly and designed properly, and then following all the way through with the mechanical contractor side to make sure that it's installed correctly and meets all those expectations that were sold to the end user. So I'm looking forward to talking to you guys some more about the technology. From here, I'll hand it off to JS.
Okay, so my name is JS. It stands for Gene Samuel or John Samuel. I'm from north of the wall up in Canada. That is a Game of Thrones reference for anyone. So I moved here 2.5 years ago. So I started with VRF myself 7 years ago up in Toronto in Ontario. There's all sorts of electrification going on over there as well. I moved here a few years ago when my parent company, HTS, did an acquisition and we gained a Daikin line. So we are the manufacturer's rep for Daikin, which means we do a lot of work with the engineers or the owners up front, but we also sell the equipment to the contractors. We do a lot of the commissioning and sometimes service and maintenance. I personally work mainly with engineers and consultants. We're based out of Peabody, north of Boston. So this is the agenda, the flashing agenda, it seems like. I think we'll deal with that most of the day. For today, I'll go over heat pumps. We'll go right from the basics, refrigerant cycle, heat pumps, what type of heat pumps are out there. And then Greg will go over selections. I'll talk about ventilation. Then we'll have some discussions from the MassCEC and MassSAFE folks for the grants and incentives. And we'll finish with some examples and projects. So both Greg and myself will each have a case study of a project we've done that we will go over. So first, let's go over some heat pumps and how they work in different types. So we're going to start from the top about how heat pumps work. A heat pump is no different from your regular refrigeration cycle, which means your fridge in your house or your car air conditioner all uses a refrigeration cycle. Of course, your air conditioner in a hotel, the PTAC through the wall, those are all refrigeration cycles. So an air source heat, so back to the refrigeration cycle. You might have seen this before, 4 main components in any refrigeration cycle. Again, whether it's your fridge or your car, they all have a compressor, You have a condenser, an evaporator, and then an expansion device. Anybody know where what we call the suction line is here? Which number on here is the suction line? If I heard the term before? Number 2, exactly. Suction line from the evaporator back to your compressor. The discharge line from the compressor to your condenser. Then you have your liquid line out to your expansion device. In residential mini splits, this device usually lives out in the condensing unit. In more commercial VRF, the expansion device lives in the multiple evaporators, usually. Now, what is a heat pump? Again, a heat pump is the same thing as a regular refrigeration cycle, but we reverse the flow. We go the other way. So the outdoor condenser turns into your evaporator. That's why you'll hear Greg and I often refer to the machines outside as outdoor units, because they're not always condensers. They're only condensers in the summer. In the winter, to become evaporators. So we reverse the cycle. Now, we don't just turn the flow the other way. Your flow is always going through a compressor in the same direction. We just add this component called the reversing valve. Right? So in cooling mode in the summer, we send a discharge off the compressor to the condenser outside. So real hot gas can get cooled by the warmish air outside. Whereas in the winter, we take the discharge gas and we send it right to the indoor unit, right to your coil, which is now technically a condenser. But we don't call them that. We call them fan coils, or we call them indoor units, because again, they're condensers or evaporators. We just reverse the flow. Your fridge, in theory, is a heat pump. Your fridge heats your kitchen by cooling down a little box. Right? So it is a heat pump. It doesn't matter which way you're going, in theory. So it's not nothing too much of a, there's no black box or magic box about a heat pump. It's just a refrigeration cycle going the other way. Again, here's your house. The same system in the summer is taking heat from the inside and rejecting it outside. In the winter, you take heat from the outside and you bring it inside the house. Now, somebody might say, what if it gets to 0 degrees? There's no heat left at 0 degrees. Well, unless you're at absolute 0 temperature, there is heat in the air. So 0 degrees might be cold for us as humans, especially when it's really windy and snowy and all sorts of fun stuff in the air. But for the refrigerants that we use in here, 0 degrees is just another state, not another state, but another location on the pressure enthalpy diagram. It has a little less heat, but it's still got plenty of heat. We'll talk about that later and how it affects efficiency and capacity. Again, there's big freezers out there. Those are heat pumps. They cool the freezer to heat the outside using very cold air, because freezers get down to what, minus 30, minus 40, especially industrial freezers. So the concept of heat pumps, even in very cold weather, is not new. Now, the word heat pumps gets used for different things. There's what we call water-to-water heat pumps. Those can get used sometimes if you're trying to electrify your domestic hot water. So, for example, I have a geothermal loop. I want to use that to make hot water. Well, geothermal loop, the water will never come out of the ground hot enough for domestics. I need to raise that temperature. So a water-to-water heat pump, again, moves heat from colder water, which is geothermal, to the hotter water, which is domestic. So that is a water-to-water heat pump. It does not interact with air at all. It just goes from one water temperature to another and raises that heat, again, using a compressor and an expansion valve and an evaporator and a condenser. But they're not coils. They're usually coaxial heat exchangers, tube-in-tube heat exchangers. Then there's the water-to-air heat pumps. That's what's commonly known as a water source heat pumps. Right? There's the horizontal versions, common for office buildings, general areas, usually up in the ceiling. They go as small as a couple tons. They can go pretty big. You can get a 10-ton water source heat pumps, even larger sometimes. And then the vertical heat pumps, typically for condo buildings, maybe a third to half of the new build residential condo market, and especially mid-rise, high-rise, probably still use water source heat pumps or some version of them. Now, usually a water source heat pump is, again, refrigeration cycle, everything's in here. The compressor, the expansion valve, the evaporator, and the condenser, they're all in here. There's 2 heat exchangers. One is the coil with the air. One is a coaxial heat exchanger with the water. So these things interact with what we call a condenser water loop. So in the summer, when all these heat pumps are taking heat from the air and putting them in the water gets too hot, you turn that cooling tower on to maintain a certain temperature on the water. In the winter, all these heat pumps go the other way and they extract heat from the water loop and they put heat in the air, so that water gets colder and colder and colder. Eventually, you got to turn on a boiler because the heat can't come from nowhere. It comes from a boiler to maintain a minimum temperature. But you can also connect these to a geothermal loop. So if a heat pump is connected to a geothermal loop, that's the name. We call them ground source heat pumps. So if you've heard of the term ground source heat pump, it's no different than a water source heat pump. Some of them have different ranges, maybe different compressors, but very similar concept. So with a geothermal loop, of course, that condenser water can get maintained either fully or partly using the ground loop. And then we get into our favorite, at least Greg's and I, and a lot of people in the room, which is the air-to-air heat pumps. In theory, there's some PTACs, which are through-the-wall units in hotels, that are air-to-air, because they take heat from the room in the summer and throw it outside. But some of them come in heat pump functions, take heat from the outside and throw it inside. But the technology in here, the size of the condenser coil, don't allow these to work down to very, very cold temperatures, so they're not very, usually they have electric heat in them or even gas heat as well. But that's an air-to-air heat pump, or it can be. The mini split and the multi-split is the residential, light commercial version of an air source heat pump that we call it. Again, all the components of a refrigeration cycle is there. That's the outdoor unit or the condenser in the summer, indoor unit or the evaporator in the summer. Again, condenser, evaporator, the terms change depending on what you're doing. And then in these units, usually the expansion valve lives out here and the compressor is outside in the condensing unit, always very common. This is a multi-split here, so one machine can connect to 2, 3, 4, or 5 or more different indoor units. So that is your typical air source heat pumps. Lots of developments in the past decade in terms of technology, both how low they can heat, defrost technology, and all these things to make these more efficient and even better. The concept that, oh, heat pumps can't work below 32 is a very, very outdated thought. These units go down to the -4s, -13s, -20s. Go ahead. Package terminal air conditioner. So it's this, you get into a highway hotel, you got that unit under the window that turns on, is real loud. Those are just package terminal air conditioner, a very big replacement business. Still exists for highway hotels. It's still probably the cheapest heating and cooling system you can put in terms of capital cost up front. The question is, where does it get heat when it gets very cold? As I mentioned earlier, the colder it gets, there's less heat in the air, but there's still a bunch of heat unless you get to, I guess, absolute zero temperatures. So at -20, there's still a lot of heat in the air. For you, it's cold. For me, it's cold. But for these, there's still heat there. So there is no resistance heat in an air source heat pump unless you purposely go in and add it. Somebody can say, hey, especially up where I'm from in Canada, where our design temperatures get really cold, somebody might say, I'm going to add a baseboard electric heater, and I'm only going to turn it on, and these can control it if I need it, if for some reason that can't keep up. So you can always add electric resistance as a backup, as a belt and suspender, safety system. That's 15 years ago, 10 years ago, that was very popular on these systems. It's becoming less and less popular just because of the reliability and the range that these can go down to. Sometimes people will do a hot water as a backup, especially a retrofit. I already have radiators that do hot water. My boiler is decent, so let's just leave those there, and we'll put a VRF or air source heat pump in, and I'll only use those if I need to, or on certain days when it's really cold and cost-wise it might make sense. We'll talk about that a little bit later. But as a basic system, an air source heat pump does not come with electric resistance heat. The compressor itself that operates, the way that it generates heat is it moves heat from the outside to the inside, and you power it with electricity. There is some losses. It's not 100% efficient. So there is some of the power that goes into your compressor does get thrown in the refrigerant as some heat. So that helps you in heating. In cooling, it hurts you. You have to reject that extra heat. So you do get some help from electricity use of the compressor. Then we get to our favorites, which is the commercial versions of air source heat pump, which is VRF, or variable refrigerant flow. VRF is essentially a larger version of this mini-split, multi-split outdoor condensing unit that can connect to 3 or 10 or 30 or 60 indoor units. And you can twin them. Here's one machine. We can put 2 or 3 machines. Usually don't go beyond 3, and make them into much larger systems, 20 tons, 30 tons. Now, a big difference between a multi-split and a VRF, because the VRFs also come in smaller machines. They also come in machines that look like this one. A multi-split is home run piping. So every unit is piped back to that outdoor unit. So they're limited to maybe 4 or 5 units, and they only go up to about 4 or 5 tons of capacity. Call it a big house kind of thing. Well, big is relative, a few thousand square feet. With anything VRF, everything is in series, which means I take pipes, I go into the building, and from there I'm going to tee off and feed all sorts of indoor units. Let's go through the components a little bit. Again, the indoor units, there's all sorts of different types. The concept that air source heat pump is a wall-mounted type of unit is also an older thought. About 50% of the VRF market uses ducted units, whether it's horizontal, whether it's vertical, whether it's console. Greg later will go through all the different types of indoor units that you can have in the VRF world. We do have the wall mounts that you're used to, those wall mounts up high wall units. There's cassette type units. There's all sorts of different indoor units. And in here, you'll find that expansion device, that thermal expansion device, one of the 4 components of the refrigeration cycle. In VRF, we call them electronic expansion valves, and they're not mechanical. Thermal expansion valves, we call them. Basically what that means is they're controlled by a controller. So this controller looks at the refrigerant temperatures in and out of the coil, and it decides what it wants the valve to do. So what I mean by that is each of these valves is about a 1/4 inch thick and opening, circular, and has about 2,000 positions. So this unit knows exactly at any point in time how much heating or how much cooling that room wants, and it throttles that valve open and close. So it might say, I'm only 20% open, 40%, 60%. So you kind of run these. Usually the air runs all the time. You're just always rolling that fan, but the expansion valve decides how much heat or how much cooling you get. And each of these fan coils or indoor unit does the same thing. They each have their own controller, their own thermostats, and they each decide, do I want more cooling or do I want less cooling? That's the variability of these systems. Then you've got refrigerant piping that connects all these indoor units back to the outdoor unit. We'll talk about this a little bit later, but the fact that we use refrigerant to move heat around the building means that we can move the same amount of heat in a lot smaller volume. So what that means is you'll see later some of the flexibility of VRF is I'm just putting little pipes around the building instead of larger water pipes or instead of large ductwork. You can use a combination of hard copper or soft copper. Again, we'll go through that a little bit later. Usually the main lines are hard copper, and the little lines going to all the fan coils end up being soft copper, which is usually 1/4 inch, 1/2 inch, or 3/8, 5/8, and much easier to maneuver. And then the center of the technology is the outdoor units. This is where you have the inverter, variable speed scroll compressors. So the majority of VRF in North America, that's the main, we call them 3-phase power and above, the main commercial version of the units, use scroll compressors, and they're all variable speed compressors. These are not digital scroll compressors. Anybody in the industry that knows what those are, digital scrolls are very different. Digital scrolls actually split the plates apart to get part load capacity. An inverter compressor means there is a VFD on the compressor. So it'll actually slow down the compressor at part load and speed it back up. What happens though is that this unit here, it's wired and it sees what all the different expansion valves are doing. So at any point in time, this guy out here knows that this one is asking right now for about 12% refrigerant. This one wants 30%. This one's at 60%. It knows exactly how much refrigerant is required. So the compressor, the VFD, or the inverter is going to ramp up and down to deliver the exact amount of refrigerant required at any point in time. Hence the name variable refrigerant flow. The outdoor unit varies the amount of refrigerant it delivers to the space in real time based on what the expansion devices are asking for. That's VRF in about 3 minutes. That's the basis of it, and everything builds from that concept. There could be one compressor, there could be 2 compressors. Depends on the manufacturer, depends on the size of the machines, and they're going to stage each other, but each compressor is variable speed. So if you're at 50% load, it might run one of the 2 compressors at full speed and the other's off. Or a manufacturer might say, I'm actually more efficient running both compressors at 50%. They all do internally, they all optimize their technology that way. Same for the fans. The condenser fans are all variable speed fans. If you've ever looked at a condenser on the roof, you can see the top of the fans rolling, the regular stamped sheet metal units that are quite loud. This is different. These are all polymer aerodynamic fans. They're extremely quiet, and they're all variable speed. So this side of the heat exchanger, the fans, the outside air, also varies up and down based on all sorts of things. What's my load? What's my outside air temperature? Long story short, the variable speed compressor, the variable speed fans, the variable expansion valves that open and close based on demand is what makes these systems perform at part load conditions. These are all optimized. VRF manufacturers these days don't really care how good we do at full load. On your July 31st, 2 p.m., 95 degrees outside, at that point in time, which we call the full load or the peak design, which happens less than 1% of the time, they're pretty good, but that's not what they care about. They care about the 99% of the year that you operate at part load. So that's why you'll see later in the efficiency standards, the industry has followed and said, okay, well, we're going to judge you on how good you do at full load, called the EER, but we're going to make a real rating called the IEER that looks at how good do you do at 75% load, 50% load, 25% load. And so that's how we judge them, and that's what manufacturers really work towards is part load efficiency. And that becomes important in the conversation later. So VRF is pretty good at full load. It'll beat most things, but part load is where the magic really happens. The IER, I'll go over that later. The IER is a weighted average of the efficiency of the system at 100%, 75, 50, and 25. So it counts your full load for 1%, it counts your 75% load for 30%, your 50% load for 40%. It's a weighted average based on average hours that a building spends at different loads. So it's a standard across the board. So it's a mix of those. Okay, if there's two technical things you remember today about VRF, it's the two types of VRF systems, which is heat pump and heat recovery. One's also called a switchover system. This one's also called and the heat recovery is also called the simultaneous heating and cooling. Let's start with the first one, the basic one, which is the two-pipe heat pump switchover system. What that means is this machine out there is either in cooling or it's in heating mode. There's two pipes for all manufacturers. There's two pipes that go out to the system. One's a supply, one's a return. Again, it's liquid and suction, or it's hot gas and liquid, depending on the mode. What that means is if I'm in heating mode, that's my discharge pipe. I'm sending you hot gas, and if you want heating, you can get heating. You can decide, right, that each expansion valve can say, I want more or less heating. But you can't get cooling right now because I'm just giving you hot gas. And the blue line becomes the return, the liquid return line. And if I go into cooling mode, the opposite happens. This condenser is just delivering you liquid refrigerant. So you can take it and expand it and cool the space, and you can tell me how much you want of it, but that's all you can do. You can be off, but you can't be heating. There's no heating available. So kind of like a two-pipe chiller fan coil system. You're either the chiller's on and you're in cooling in the summer, or you've turned your chiller off and it's winter period and your boilers are on and you're only in heating mode. Now, a couple advantages of this system versus a two-pipe chiller fan coil system. One of them is I might have multiple of these systems in a building. So I might have one system serving all my north classrooms or all my north suites in a multi-res building, and one system serving the south. So what that means is all the units on the north can be tied to one machine that's going to be in heating mode on today and in the afternoon, for example. Whereas on the south, I can have a unit that is facing the sun. They're all getting warm, so I can have that system in cooling mode. But within the system, all the south units, they're all in the same mode. That's one advantage. So now I've zoned my building a little bit. I don't have just one chiller for the whole building I turn on and off. I've got multiple systems. Some buildings can have 50 VRF systems. That happens. If we're talking about a 1,000 suite hotel, which exists out there with VRF, there's multiple systems and they're all zoned. The other advantage too is I don't need to go turn a chiller on and turn a boiler on and turn it off. This will switch over automatically. So because this condenser knows exactly what's going on in each unit. So if it was in heating in the morning, like this morning, right? We woke up, it was high 40s, low 50s. It's in heating mode because all the set points are at 72. The rooms are a little cold. It's all in heating mode. When the sun comes around, like it will this afternoon, and it starts to get warm, it's going to see all the room temperatures go up. So it's going to say, okay, now on average, I need cooling. It'll switch 5, 10 minutes. It'll do automatic switching, and it'll start going into cooling mode. There's all sorts of algorithms that different manufacturers have as to how you program that. Well, when do you switch over? Do you wait until there's much of a difference, a small difference? Is it an average? There's all sorts of ways of doing that. You can even make one count for more. This is the boss's office, so if that person wants heating or cooling, they get heating or cooling. You can always weigh things like that. So two main differences between this and a chiller fan coil system is that there's multiple systems in the building, usually, and they switch over automatically. So what that means is on a warm December day, you'll get cooling. Whereas in a regular two-pipe chiller fan coil, you're not getting cooling. If it's warm in December, those chillers have been long gone, off. Now the heat recovery system, probably the most famous VRF system, also known as the simultaneous heating and cooling system, is the one that allows each and every indoor unit to heat and cool independently and simultaneously. Now, multiple manufacturers do this by introducing a third pipe into the system. Some don't. We'll talk about that in a minute. All manufacturers do introduce another component called a changeover device, a branch selector box, a branch controller box, has different names for them. So the way this works is essentially in this changeover device is usually a set of valves. Sometimes it's a heat exchanger, depending. So what happens is in a three-pipe system, there's always a hot supply, a cold supply, and a common return. It's liquid, suction, and hot gas. So if this unit here wants cooling, this changeover box knows that, and it'll say, okay, here's the cold supply for you, and I'll take back return. Whereas over here, this changeover box sees that its fan coil wants heating, so it'll do the opposite. It'll switch over the other way and say, here's the hot supply. That's how this one can cool while this one can heat. Now the good news is, because I'm taking heat from this space and I'm putting it in the refrigerant, and from here I'm taking heat from the refrigerant and I'm putting it in the space, there's a certain level of efficiency there, what we call heat recovery. hence the name heat recovery from the system. It's not perfect, but there, in terms of every BTU of heat from this room doesn't go into that room. It still has to go back to the condenser, go through the cycle and all that, but there's definitely some efficiency gains in doing that. I don't think I've seen yet in my career somebody decide to go from a heat pump system to a heat recovery system for the sole purpose of the energy efficiency of the heat transfer. The decision is usually on, does my building need independent, simultaneous heating and cooling in all my units or not? A school might say, yeah, okay, put 4 classrooms that face north on one system, and that's fine. I don't have to heat one while I cool the other. That's okay. But a hotel will say, yeah, it's a hotel. I need every single room to heat and cool independently no matter what. I can't have calls saying I can't heat right now. Oh, that's because most of your neighbors want cooling right now, so you're just going to have to wait. You can't do that in a hotel, right? So that's usually the difference. There's a 20 to 30%, it all depends, cost premium to go from one to the other. Because A, you got to add changeover devices, you got to add piping, whether it's a 2-pipe or a 3-pipe system, it overall adds some piping. The machines, too, have more technology in them. To the naked eye, they'll look the same. A 10-ton heat pump VRV or a 10-ton heat recovery VRV will look the same to you on the roof, unless you look at the model numbers. You open it up, though, there's more reversing valves, there's more things going on in there, so there's a cost difference there. The fan coils are the same. A 2-ton ducted fan coil that's tied to a heat pump or heat recovery system doesn't matter. That fan coil is the exact same. So as I mentioned earlier, different manufacturers do the heat recovery systems differently. The 2-pipe heat pump systems, schematically, are very, very similar across the board from manufacturers. Okay, good question. So VRV is a trademark. It's a brand name. So it's a global trademark. So it's just for me, I'm with Daikin, and VRV is Daikin's brand name. It came from their original trademark back in '82. VRV is just, that's like Kleenex. It's like my brand name. VRF is the industry name. That's what ASHRAE, AHRI refers to. So I'm supposed to use VRF. If you ever catch me using VRV again, please don't say anything. I'm just kidding. If you catch Greg saying VRV, then we got some questions. But thank you. VRF is the proper industry term. So like I said, in heat recovery, different manufacturers do it differently. This on the left is a 2-pipe system where they actually do the whole thing with 2 pipes to the main central larger branch control device. 3-pipe manufacturers can use a mix of single branch control devices at each unit, usually more common for multi-res, mid-rise, high-rise buildings, or a mix of both. It's 3 pipes, but they use multi-port branch boxes. Everyone's got their pros and cons. Everyone's going to look at your building and optimize which method to use depending on what. Some manufacturers can use multiple of these. Some are limited to one. That all depends on the manufacturer. Most top-line main manufacturers, have found a way to optimize a building and the amount of piping and the install cost to each other pretty evenly using the different systems. There's obviously sweet spots for each. So I'm going to go over some benefits generally of heat pumps. This is more of an agenda for the next slide, so I won't go over all of this, but I do want to talk about flexibility a little bit, and we will finish on efficiency and operational cost. One of the big things about VRF, I think one of the reasons we're here today, is VRF is essentially, in our minds, Greg and I, in our biased VRF minds, the way to electrify a building on the HVAC side. So for states like ours and others, and other countries like Canada that are electrifying, if you're going to heat your building with electricity, an air source heat pump in 90+% of cases is going to be the way to go. And a big part of that is the COPs, which we will talk about. But it's also because what's the alternative? If you want to heat with electricity, you can put baseboards everywhere. That's 100% efficient, COP of 1. The problem is electricity is very expensive, so it'll cost you a whole bunch of money. You put an air source heat pump in with the same amount of electricity, you can deliver 2, 3, 4, 5, or 6 times more heat. We'll talk about that in a minute. So that's why air source heat pumps are so popular. It's the way to electrify your building on the HVAC side. You'll see in the fresh air discussion later, which is the other side, right? These things do heating and cooling for your space. Fresh air is a big subject. There's also ways of electrifying that with using this type of technology. Here's an example of a building, right, where they've got solar panels. That looks pretty small for the size of the building. Maybe they've got more on the other side. But they got solar panels, and they got air source heat pumps here on the roof, which means this panel can feed in time with battery backup or with other methods, the air source heat pumps, which in turn deliver cooling in the summer and heating in the winter. That's a big part of the subjects of even in the mini splits and the multi splits residential. That's the way to electrify your house, your building, commercially, VRF is the commercial version of that. This is the way to electrify your building. There are other methods of electrifying your buildings. A properly sized geothermal loop with proper equipment can work. There are larger versions of air source heat pumps that exist that are not VRF. So we're not saying we're the only way. We're just saying we're the best way. No, we're just saying we're a very good way of doing that. Now, one thing to remember, VRF is a zoning system. If somebody comes to me and says, I have a big warehouse, it's 10,000 square feet, and it's all open, I want to do VRF, we're going to go, ooh, it might not be your best bang for your buck. Because VRF is all about multiple smaller, they can go up to 8 tons, which is pretty big, but usually smaller fan coils that go in and zone your building. A building like this that we're in, that's a zone building. This is a bigger one. I might have 2 units in this room, but I might have offices upstairs, all different zones. That's where it makes sense. A big open area, that's where alternative equipment that can do 50 tons, 100 tons at once might make more sense. So whenever you see zoning, whenever somebody says, oh yeah, we have these big rooftops, I got 3 big rooftops, but I want to start zoning this building. So, they're going to have to go with VAV, with reheat and controls. That's where you say, oh, maybe VRF might make sense. If somebody says I got 3 big rooftops and I'm happy with 1 thermostat, the whole floor of my building, and I just want to replace it, you're going to say, sure, go ahead and replace the rooftop. Because VRF, if you're not looking to zone it, VRF becomes quite an expensive way of doing that. So VRF is a zoning system. The next thing we talked about a little bit is the sizing and the flexibility of the system. This is just an example, a visual of 20 tons of cooling. 20 tons of cooling, for example, with air. So picture this as your VAV system would be this big. Your central air system, similar idea. Your chilled water system, you might use a 4-pipe system, especially if you want to give independent heating and cooling. With a chilled water system, you need a 4-pipe system. That could be a water source heat pump. You're going to have these water pipes, 3-inch pipes. All of them are hard copper, plumbing copper. With VRF, you're going to be using maybe 1 3/8, 1 1/8 for 20 tons. That's it. 2 pipes. You get insulation around them, usually 1/2 inch or 3/4 inch Armaflex wall. So if you look up and you see VRF pipes, you're going to see what looks like 2.5 inch black piping. Well, you're looking at insulation. The pipe itself is usually 1 inch, 1 3/4 inch, 1.5 inches, maybe the largest you'll see, and they go as small as 1/4 inch. So even if you see a pipe that's 1 inch, it's probably got a 1/2 inch copper in there, and it's got a 1/2 inch wall insulation. So the size of these units makes VRF very prominent for a retrofit. If you are in Massachusetts, especially closer to Boston, there's a lot of retrofit projects. Somebody wants to retrofit an old school building, an old house. It'd be very hard to go in there and plow ductwork through the whole house, but little pipes is much easier. That's one of the big benefits of VRF. Let me go back here. And again, usually with VRF, the main lines from the condenser might be hard copper, because 1 3/8 and 1 inch, you're going to run hard copper. Once you get in your building, let me go back quickly. Sorry, I'm jumping around. I want to go to these slides. Once you go inside your building, from the branch box onward, the distribution might, or here, all the small pipes are usually going to be soft copper. Why? Because each of those is feeding a fan coil. Maybe that's as big as 4 tons or so. You can carry 4 tons in a 3/8, 5/8 pipe, which is soft copper. So you run usually hard copper from the condenser down to the branch boxes, branch control device or changeover devices, then you can run soft copper. I'm going to fast forward here. So this size of pipe is only the main pipes. They get much smaller when you get inside the building. Let's talk about efficiency a little bit, and I'm going to break it down looking at the cooling side of things. Basically, almost all methods of cooling in the world, no matter what system you're using, in some point in the system use a compressor, a refrigeration cycle. Whether it's a chiller, even a geothermal system uses a compressor, because the heat pumps they use compressors, the air water source heat pumps. So they all use a certain version of the refrigeration cycle. Heat pumps, air source heat pumps, also do that, but again, they use that in heating as well. So what that means is, excuse me, let me get through this. We talked a little bit about the EER. The EER is an efficiency measurement. So AHRI, which is the body that governs this, says, okay, manufacturer A, give me your unit. I'll run it at full load. There's certain standards, and I'll figure out how many kilowatts of electricity you need in to deliver a certain amount of cooling. That's what it does. That's what the EER is. They test almost everything has an EER rating, a water source heat pump, or whether it's VRF. Typical values for us is in the 12 to 15 range, us being the VRF folks. However, that only happens at under 1% of the time. For a generic building, this building, the equipment in this building right now, which I don't know what it is, I haven't looked at it, but is sized for peak load. This building is sized on July 31st at 2 p.m. when it's the hottest day of the year, at least in the books, right? Hottest time, the equipment size to keep that building satisfied at that point. So it's that size. Every other time, like today, this equipment is running at, today, especially at part load, maybe 20% load. So what happened is, in 2010, 9 years ago, AHRI looked at this and said, especially these VRF systems are really designed for part load. Let's take a look at the EER at different load points. That's what the IEER came from. So just to compare, the IEERs of, of VRF systems range from 16 to 26, an average being in the low 20s. So if somebody's asking you what the EER efficiency of VRF is, and that's all they're looking at, they're not getting the right picture, because they're going to see 12.8, 13.2, and they're going to say, isn't that the same as, can't I get a packaged rooftop unit that's pretty cheap for the same EER or close? And you can say, yeah, you can. But it's the IEER that's the big difference. What that means is VRF systems are almost twice as efficient at 50% load than they are at full load. That's both for cooling and usually for heating. Now, let's look at heating. Most heating methods don't use compressors. Most heating methods use some sort of fossil fuel, whether it's a furnace, whether it's a VAV rooftop unit, a packaged rooftop unit, whether it's a boiler, they all use some sort of fossil fuel. So a way to figure out how efficient the systems are, instead of EER in heating, it's common to use COP. It's actually the same thing, it just uses different units. It's heat supplied over work required and all that. Just so you know what that means, a 90% efficient furnace has a COP of 0.9. That means that for every unit, BTUs of heat from gas that you put into it, 90% of it goes out as heat. There's a few losses in there. That's a COP of 9. An electric heater is 100% efficient. Right? Every kilowatt of electricity you put in there goes out as heat. There's almost no losses. It's essentially virtually perfect. The problem is the fuel cost difference. Gas is cheap, electricity is expensive, generally, especially in comparison in our market. A big part of the next part of the conversation is about your crystal ball, everybody's crystal balls and political views, and what's going to happen in the next decade on the prices of both. Right? And there's people that have assumptions or predictions for both, how gas will go up or down, electricity go up or down. A lot of us in this world are believers electricity will stabilize or go down in the future, and especially the cleanliness of the grid is going to go up, the addition of renewables, all that's going to be helpful, and that gas will potentially go up as carbon taxing comes in and other things. So when we look at a heat pump system, air source heat pump, the COP values, remember the gas furnace is a 0.9, baseboard's a 1. The COPs, the average COP of an air source heat pump is around 3. Now, unfortunately, COP is a full load value. That's the same thing as looking at the EER in cooling. It's not very good. That's how that COP, basically, when AHRI looks at it, they do the same thing. Give me your unit, Mr. Manufacturer. I'm going to see how many kilowatts of electricity you need to generate X amount of heat at different temperatures. But it's making that thing run as hard as it can at full load. So unfortunately, we don't have what we like to refer to as an ICOP, which is a COP at 75% load, 50% load. That doesn't exist yet. So heating, it makes it much harder for us to be able to demonstrate that, yeah, even though gas is a lot cheaper than electricity, by a ratio of 3 or 4 or 5, our COPs are 2 or 3 or 4 or 5 at full load and way more at part load. That's very hard to demonstrate. But even looking at just full load values, if you start to graph it, you come up with what we call a transition temperature. And that addresses this gentleman's question earlier about where the heat comes from and how well it does it when it gets cold. There's a certain temperature below which your high efficiency boiler or furnace is cheaper to run than the air source heat pump. And that temperature is very, very dependent on the cost of electricity. So that's where education is important to explain to a customer, whether it's a residential homeowner or a commercial building. You're buying an air source heat pump, which means that right now, today, with the prices you pay below 23 degrees Fahrenheit, let's say, I'm going to pick an average number, down to 23, your heat pump's cheaper to run. Below 23, you would be better off with the furnace. But there's not many hours below 23. Don't forget, these are pre-wind chill temperature. Wind chill, we talk about later, our condensing units don't feel wind chill like us and our skin. So what that means is overall, you're still going to win generally. And in the future, you're going to continue to win even more as these utilities hopefully even out. Oh, this is everything I just said, I think, in a slide. Just so you know, on the coldest design days, whether you use 7 degrees, 0, even if you use -4, around that range, people ask me, okay, what's your COP at 0? Doesn't the COP get down to 1? Well, it doesn't. So even at 0 or -4, the COPs of commercial air source heat pumps are going to sit around 2. So yes, at that point in time, on that day, at 0 degrees, on January 31st at 3 a.m., I'm making these dates up as a typical coldest day of the year. On January 31st at 2 a.m. when it's 0 degrees outside, your COP is going to be at around 2. At that point in time, if you had a high efficiency furnace, you'd be better off using that. But how many hours a year does that happen? And the rest of the year, you win the air source heat pump. So unless you want to install both, which you can, and control between both, the air source heat pump usually still wins. I have this. I just show what the different AHRI ratings are, EER, IEER, but that's basically all of it. Are you asking for what the formula is?
Yeah, the blend that you said is like.
Yeah, it is. Yeah, sorry. You know what? Good idea for me to put that next time. If you literally Google IEER rating, within the first 3 hits, you're going to get the formula for it. It's 1%, 37%, 48%, 42%, and then the last one is 20, something like that. And the formula is going to be A times 1%, B times whatever, and the ABCDs are the EER values at those points from manufacturers. Now, I'll use this as a way to talk about IEER in our minds is already a little outdated. What I mean by that is that's 9 years old. So IEER, even though it looks at how well you do at 100% load, 75% load, 50%, and 25%, the technology's gone beyond that. 9 years, right? As you can see, in the past 5 years, and I refer to it as cruise control. So now the VRF manufacturers have really looked into optimizing cruise control. What I mean by that is if you go in a car and the cruise control program says, I want to go 60 miles an hour. Your cruise is just going to stay 60 miles an hour. If you're going up a hill, it'll downshift and work really hard to keep you at 60. And if you go down a hill, it'll press the brakes to keep you at 60. It's not very efficient, but it'll keep you at 60. So an intelligent cruise control would say, you know what, I don't care if you need to go just 55 up hills, and if you go to 65 down a hill, if it saves energy, don't downshift, go up intelligently, I'll be okay. And if you're going down a hill, I'm okay going a little bit faster. Don't waste energy and press on the brakes, right? It's an intelligent cruise control that's more efficient. So that now concept exists in VRF. And the speed here is your room temperature. So we can program and tweak our systems now to say, okay, I want 72, but you know what? If you're on a peak day on July 31st and that room needs to go to 74 for a few hours, I don't care because that's going to save me a lot of energy. So this cruise control, and it's usually used with varying the target evaporating refrigerant temperatures and all of that. So that's great. We have all that. It makes our efficiencies and way better. But when you go to AHRI and you test for IEER, they tell you, no, run your thing at 60 miles an hour all the time. They don't let you play with all these tweaks that we can do. So all that to say, IEERs is already a little outdated because there's so much development that's happened that it's not reflected here. We're still stuck to, here's the IEER. The manufacturers now are beyond that and developing things beyond what the IEER can test. I'll go back to what I was going to show here, which is part of the efficiency, and this talks about comfort a lot, but it does affect efficiency, is the difference between an air source heat pump and a regular water source heat pump, or a PTAC in a hotel. The way those work with regular thermostats is, hey, I'm on, I want cooling, so your compressor turns on, you get cooling. Then your thermostat says, oh, I'm satisfied, turn off, so the compressor turns off, the room temperature raises up. And it hits 77 again, turn back on, off. So these become on-off systems. You've probably all witnessed this by hearing a thermostat go, that's the relay in the thermostat, and hearing that heat pump turn on, and turn off, and turn on, you feel air, no air, air, no air. That's a regular air conditioning system. Packaged rooftops are the same way. You might not hear it, it's on the roof, but they all work the same way. What we do at VRF is a little different. The thermostat itself, they're all digital thermostats, and they're actually telling you what the set point is. It'll turn it on, then as it gets close to set point, it's going to start ramping down the compressor a little bit to a point where it's going to stabilize, right? 60 hertz is the usual frequency of the grid. This one might stabilize at around 45 hertz. That's the inverter, right? Which means your expansion valve is slowly zoning in, dialing in exactly what your space needs for the next couple hours, and it changes, and it keeps your room temperature very smooth. So we have a whole comfort discussions with engineers and owners about air source heat pumps and the fact that it won't be turning on and off and wondering what just turned on. It's very smooth. There's a sound advantage to that, but there's also an efficiency advantage, right? Anything that runs steady state is a lot more efficient than turning something on and off. Again, back to the cruise control. It's like I want to go 60 miles an hour, so I'm going to go 0 for a few minutes. I'm going to 120 for a minute. I'm going to 0 for a minute, 120 for a minute. That's 60 miles an hour on average. That's not very efficient, right? This is cruise control. Let's just throttle back a little bit and go 60 miles an hour. This is what I was talking about earlier. These are the official ratings by AHRI, standard 1230 from 2010 for commercial VRF units. So EER, full load, IER, part load. We do have 2 COPs, one at 47, one at 17F, which most people use. We don't have COPs below that. The manufacturers do, but it's not an official rating. Again, these are full load COPs, unfortunately. The SCHE basically says, hey, how good are you at actually moving heat from one zone to the next when you have a heat recovery system? So it doesn't get used as much, but it is an important rating as well. This is an overview of my discussion from earlier regarding operational cost. In cooling mode, let's look at cooling only. VRF is essentially more efficient than any or most conventional systems. What that means is if you had a downtown Boston office building that's 30 stories and you were going to build a 5,000-ton chilled water plant with magnetic bearing chillers and VFDs on pumps and cooling towers, and you optimize that plant, very important, you can beat VRF at the end of the day. So VRF, you can beat that with big systems, with well-engineered systems. There are systems out there that can beat VRF for sure. But usually those are in the larger sizes. You're not going to do a magnetic bearing chiller on a 40-ton building, right? That's where VRF really dominates. So in most sizes, a couple hundred tons and below, VRF is going to be your best bet for cooling efficiency and cooling operational cost. This building being an example. Which means it's going to be less expensive to operate than most other systems because we both use electricity. Almost all cooling systems use electricity, whether it's your chiller or VRF. Now on the maintenance side, we don't talk about this too much today. We can answer questions about it. Maintenance is usually one of our talking points with VRF. It depends what you're comparing it to. If you're comparing it to water source heat pumps, there's a big discussion about you don't have 100 compressors that are in your spaces everywhere in the heat pumps. We have 4 compressors up on the roof. There's a maintenance advantage there, reliability and all that. Also, there's no water to maintain. Water source heat pump, you have your towers, your boilers, your pumps, heat exchangers to maintain chemical treatment on the water. With VRF, there's no water. You don't maintain the refrigerant. We don't even have filter dryers in the pipe to change out. We don't want filter dryers in there. It's all internal to our systems. So there's a big maintenance discussion there. Now in heating, we talked about VRF being much more efficient than almost any systems by 3 or 5 times. That's the COP. But we're cheaper to run than electric resistance heating. But we use electricity, not gas. So overall, the discussion about what's cheaper to run in the winter between VRF and conventional systems is that discussion about transition temperatures and costs of gas and electricity. Overall, in our market, VRF is going to win or be on par with conventional gas-fired systems, traditional efficient gas-fired systems, with the temperatures that we have and the electricity prices that we have. As soon as gas goes up, or as soon as electricity stabilizes or go down, that number gets better. The opposite happens, that number gets worse. And again, similar savings potential on the maintenance side of VRF. On the heating side, there's no hot water to maintain. Overall, your air source heat pump is going to be more efficient and usually cheaper to operate, despite our current prices here. Up in Ontario and Canada, our ratio of gas to electricity is often worse. Worse meaning gas is even cheaper and electricity is more expensive than here, and air source heat pumps are still very, very popular despite it being even colder. So we're not, Boston and the Northeast is not the first precedence of doing air source heat pumps in cold climate where gas is cheap. We're actually in our minds a little bit behind in doing that, but I think that we made a lot of progress in the past few years with incentives and different groups out there and the different manufacturers. So I'm going to let Greg finish my part of this section here. This talks about capital costs and upfront costs, and then he'll go into his section. So I was just comparing. So on this side, I'm comparing a VRF system, which is an air source heat. Oh, yeah, good point. So I think the question was about what I'm comparing VRF to with water source heat pumps. So in this section for cooling, or in both, I'm comparing VRF, which is air source heat pumps, with potential conventional systems that you might be comparing it with. I'm poking a bit on the multi-res commercial buildings. So I'm using water source heat pump, chiller fan coil systems, those types of central systems. But VAV can also be used in these comparisons. So in cooling, generally VRF wins, which means operationally we win. In heating, we always win on an energy approach. But again, we're using gas, electricity, not gas. So then it's a debate about transition temperatures. Does that address your question a little bit? The question was, I talked a lot about the VRF, which is the commercial version, which can be residential as well. And the question was about the efficiencies of those versus residentially. We may have similar answers to this. I'll let you maybe do it after I answer, Greg. It is my belief that the commercial systems lead the way in terms of efficiency. The size of the coil, the technology that's been involved in the different multi-circuited coils, defrost technologies, A lot of it, just because of the size of the unit, we have the ability to do that in the commercial machines. So the commercial machines, in my mind, are more efficient in cooling and in heating. However, there's been a lot of improvement in the residential side as well. You've seen the addition of cold climate. Cold climate exists in commercial units, but cold climate machines exist in residential as well. So that technology, and that's new over the past 5 years or so, 5, 6 years. So that efficiency has gone up. But if somebody was to say head to head, which one is more efficient and COPs and all that, I would always put my money on the commercial systems. Also, we pay a lot less commercially for electricity than we do residentially, which means the argument of transition and versus natural gas is even stronger usually, or is very strong commercially because of that electrical rate. Gas usually being more similar. Correct. So the question refers to actual field-tested efficiencies and field-tested performance of units. And yeah, there has been some testing done residentially. That doesn't exist commercially. I wish it did. And commercially, everybody's got their own, every manufacturer has their own stories, case studies, and owners that have it that can speak to it, but there's no public third-party testing that was done that way. One of the things about the residential testing, what happens is, and this is where education is quite important, is an air source heat pump its efficiency is very dependent on what temperature you're trying to maintain indoors, right? So if you have a furnace and if it's 0 degrees outside, whether you try to maintain 70 or 75, of course you'll need to run it longer for 75, but the efficiency at which it does so is very similar. You're just running it more. With an air source heat pump, residentially or commercially, if it's 0 degrees outside and I'm trying to maintain a space at 75, 76 versus 70, that makes quite a bit of a difference. And that goes back to the refrigeration cycle, the heat pump cycle, and the refrigerant temperatures and the compressor lift that means, the impact on that. So all that to say is usually, Greg and I's claim will say, any rating you see on paper done in a lab, like you said, is usually very conservative. Especially these Japanese brands where a lot of these come from, they're very conservative. We often like to see units outperform that. Part of it is because of that cruise control and the analogy I was using earlier. We go well beyond what the testing can do. But whenever I hear somebody come back and say, hey, this is costing me more than I thought, or if a third-party test says, hey, this is costing us more than we thought, we look at, well, what are you trying to maintain here? Are you doing proper setbacks? Not huge, but setbacks. You look at the control side of things. That's what I see whenever the field comes back with less than expected, because usually you should win versus the books. Hopefully that answers your question somehow. Greg, I'll pass it on to you. I don't know if you want to comment about the efficiency.
I'll make a comment about the mini split versus VRF efficiency side. This goes on you, but falls off. Okay, cool. So to give a point of view, I hear that question come up a lot when the conversation is, okay, I have a 40-unit multifamily residential building. Do I use all mini splits or do I use a single VRF system, and what will be more efficient? And I agree with JS's answer. In general, the commercial equipment's going to have more technology and more advanced technology packed into it. If you got to think, a lot of the residential equipment is really simplified equipment that's made for easy installation to fit the majority of the people who are buying them, whereas the commercial equipment comes with all the bells and whistles because it needs to be a lot more applied and a lot more customizable. But in general, the biggest reason for the efficiency of these systems is the inverter-driven compressor, the variable speed compressor. Both technologies are using that same compressor technology. So VRF and mini splits are both using variable speed compressor technology. And although the commercial equipment might be more bells and whistles, more efficient itself, installation plays a massive role in how efficient the system is going to be. Are we comparing a central VRF system with 300 feet of piping between the outdoor unit and the building itself to a bunch of mini splits that are installed on the patio of every single unit with maybe 15 feet of piping? That can make a difference in your efficiency. So it's very hard to give you one rule of thumb and say this is going to be more efficient than that. It really does come down to the installation and the design of the building. But in general, the commercial stuff has a lot more technology packed into it, but the main focus of where that efficiency comes from is the same across the units. So I'm going to talk a little bit about, I'm going to continue on this. JS just talked a little bit about efficiency metrics and efficiency versus cost. I'm going to go a little bit into first cost and things to consider. And then I have a few more things after that. It is probably going to be about a half-hour section until there's a break, so there will be a break halfway through this if anyone's starting to get antsy for that. So This slide here is made to be very, very generic. And the reason for that is installation costs or first costs can depend on a lot of different things, the system design, the building itself, what you're comparing against. We're making some broad generalizations here of equipment type. What I really want to do is put in your mind the general rule of thumbs, general thought process behind these, so that when you're looking at a project, you can make sure that something's in the right ballpark. Maybe when you get some costs back, you can say, okay, this reasonably falls in what I'm expecting, but there's always exceptions. And if something's different, at least you know to look into it or ask about it. So if we look on the first thing we're looking at here is the first cost, and along the bottom side here is occupant comfort. So if we look at our two extremes, the traditional extremes of the HVAC industry, on the most inexpensive and least comfortable, least efficient option would be PTACs, packaged terminal air conditioning units. These are essentially just permanently installed window units. And although I say permanently installed, they're window units that are usually put in a sleeve in the, JS call it the highway motel. I agree with that. And they typically last about 5 to 6 years. It's usually a hotel developer that puts these in and doesn't really care how long they're going to last. They just need to sell the building. And they're loud, they're inefficient, they don't have good temperature control, but they do the job for certain applications. On the other end, you have a 4-pipe chiller boiler. I agree with what JS said before that on really large, you can get a well-designed, applied magnetic bearing chiller that's going to be more efficient than a VRF system on a really, really big building. But a 4-pipe chiller boiler generally gives you the same occupant comfort. You still have the ability to do simultaneous heating and cooling at any time, individual zone control. It gives you a very comparable system. But again, that's the Cadillac of systems you can put in a commercial building. So I really like this slide. If I've had building owners come up to us before and we're working with that say, I really want to think about using VRF in this building. Alternative we're considering is PTACs. Let's not waste anyone's time. If your budget's PTACs and that's what you're expecting, VRF's going to blow your mind when you see the price, when you see what's involved in it. There are different building types. There are different levels of what we're trying to do in a building. If someone comes up and says, yeah, I'm looking at rooftop units, water source heat pumps, 4-pipe chiller boiler, then everything's all in the same ballpark. That's where the different benefits of flexibility and installation are going to sway what's more cost effective. But if I'm going to make some generalizations, we're going to have similar efficiency and similar occupant comfort and similar levels of flexibility to a 4-pipe chiller boiler system. And I typically find that on the most buildings we do around here, VRF has a first cost advantage. When I say most buildings we're doing around here, I'm going to talk about buildings under 200,000 square feet, which lines up with what JS said about a couple hundred tons. If we look at a 400 to 500 ton building, we have those with VRF in this immediate area. Anything above that, the larger 4-pipe chiller boiler system currently make more sense. Below that is where VRF can have a first cost advantage. A lot of that has to do with, number one, the JS showed the hard water piping versus flexible copper, but also the control system required. That's actually going to be a topic of this presentation later on, is the difference in controls and how a lot of them are built in, and you don't need a complete secondary control system. You may want one, and we can work with it, but it's not required like it is with a 4-pipe chiller boiler. So that's where we'll see the cost savings there. And then if we're looking at water source heat pumps, if we look at, if I consider downtown Boston, that's where we have a lot of good data points, we're going to be equivalent, we can be the equivalent level of zoning, of temperature control of horizontal water source heat pumps for roughly the same price. And then you have situations like vertical stack water source heat pumps in some multifamily residential applications, which will be less expensive just by the way they're typically installed in the market. So that's kind of a broad first cost because it, depending on what type you use, can go anywhere. But really what I'm thinking to use this for is if someone gives you two options between PTAC and a VRF system and they cost the same, look into why that's happening. That doesn't make sense. Similar, if someone's comparing a VRF system to a 4-pipe chiller boiler and the VRF system is significantly more expensive, you're also going to want to look into that and find out why the difference is there. Did they budget it correctly? Did they price it correctly? Was there something different in the design that made them fundamentally different? Just a general rule of thumb here. And an interesting thing to talk about, JS mentioned it earlier. Yes, question before I move on. So the question was, when we say occupant comfort on the bottom here, are we including indoor air quality? I'm using occupant comfort as a very general term here for zoning. I mean, ventilation is part of it. With all these solutions, how you handle ventilation is a very similar thought process. So with a 4-pipe chiller boiler, you're typically deciding about, do you integrate ventilation directly to the fan coils, or do you use a completely separate DOAS system? Stuff like a PTAC, yeah, you have the benefit of pulling in outside air, but then you have the problem of, yes, you're bringing in fresh air, but now it's untreated, it's not using energy recovery, you're gonna have more temperature swings. So this is just trying to sum up stuff on a single slide. So I'm using occupant comfort as a general, if we're looking at zoning, you could just say, you call occupant happiness. I mean, there's a lot of different things that go into it, but in general, the stuff like ventilation is gonna be how you handle it. It's a similar thought process for all technologies on this board here. So the interesting thing to look at next would be capital cost per unit dollars. If we look at something like this, so this curve would be a typical 4-pipe fan coil. JS mentioned before, it is possible in a very large system to get something like a magnetic bearing chiller that's going to be as or more efficient than a VRF system, but it really only makes sense when you're doing a 1,000-ton building, or you're doing a very large building. So that kind of looks at when VRF came to the United States and watching its growth over the past several years, as we see the type of buildings we're involved in. Years ago, I think VRF's been in the US for a little over 15 years officially. It was used on smaller projects, renovations. You weren't doing whole building solutions with it. Whereas if you fast forward to now, doing a 200,000 square foot building is not uncommon. Even in this area, in the Boston area, across the country, doing that size building is not uncommon. So we see the equipment for VRF getting itself into a larger and larger application as the technology grows to meet the demands of the market, but also because of this capital cost situation here. So if you have a 4-pipe fan coil, you're buying a boiler, you're buying a chiller, you're buying all the infrastructure that goes with that, the control system. There's a lot of upfront cost that as you go up in tonnage, as you have more units, as you have more fan coils, your cost per fan coil, your cost per ton is going to actually go down because you have a lot of upfront costs that doesn't make sense for a smaller building, that once it gets bigger, you're just adding fan coils, you're not adding more chillers there. And similar with a 2-pipe fan coil, same exact curve, same exact upfront costs, or not same exact upfront costs, same situation, just different costs involved, so it's less expensive. Then if we look at this green line here, this is where VRF comes in. And what's very interesting about VRF is that it's a completely modular system. If I'm doing a 100-ton building, I'm probably using 5 20-ton systems. If I'm doing a 1,000-ton building, I'm probably just using all those same 20-ton systems, just significantly more of them. So your cost per unit or capital cost per unit is going to be consistent across the board. If you look at a 20-unit office building or a 20 office building or 20 suite office building, suite, mouthful there, its cost per office is going to be the same as whether there's 100 of them or whether there's 1,000 of them, because it's just, you're adding a system, it's a modular system, whereas you don't have those upfront capital costs. So you're seeing pull up the next one here, and it's a similar situation of a 4-pipe fan coils equivalent to the air-cooled heat recovery, and a 2-pipe fan coil would be more equivalent to your air-cooled heat pump. So heat recovery, simultaneous heating and cooling. Heat pump is all heat, all cool. That's the most comparable system type to a 4-pipe, 2-pipe system. So when looking at first cost, there's always going to be that crossover point where as a building gets to a certain size, it makes sense to a different technology might be more cost effective. Typically, I'd say this kind of answers the what's VRF's sweet spot. I'd say any building, definitely any building 100,000 square feet and under, VRF is going to be well within that sweet spot. Doing a building 100 to 200,000 square feet, not unheard of in this area, and it definitely shifts based on building design and what other benefits you're getting out of the system. If you're looking at a 500,000, a million square foot building, typically the 4-pipe, 2-pipe fan coils right now are going to have a greater cost advantage when you look at how that system's set up on a per unit basis. The question was, do we ever get asked or see data for a cost per ton? So yes, we often get, that's a very conventional way in the HVAC industry of describing system costs is dollars per ton. It's also a very tricky one to answer because even in the last 3 or 4 years, if you look at a building of this size, I saw this one seems to be a fairly new high efficiency building. The amount of, for the square footage, the amount of, or the tonnage of equipment needed is probably significantly less than a building of comparable size and comparable zoning that was built 10 years ago, especially with new high performance buildings, net zero, passive house. And one of the biggest factors that's going to influence the VRF system cost is zoning. I mean, I can do if we take just this space, I could put a VRF system in here with one fan coil unit, and that's a very cheap installed cost. Or I could divide this room up into 20 different zones with 20 individual offices and 20 different fan coils and 20 different thermostats, and you have a significantly different cost value there. So I typically try to push people more towards the dollars per square foot for an average zone building rather than dollars per ton, because your tonnage is going to change quite a bit depending on how good the construction is in that building. Whereas I find the biggest indicator of cost is usually zoning, and zoning is pretty kind of loosely related to the actual square footage of the building. So if you look at like VRF, I'd say a really well-zoned simultaneous heating and cooling VRF system, you're looking probably the $28 to $30 a square foot, but it could be all the way down to $20 a square foot if you're using a changeover system, more reasonable zoning, more simple system.
Does that include fresh air integration?
That typically does not. I mean, there are ways that it can, depending on how much fresh air is being brought in. That's not including the cost of a DOAS system or an ERV. If you're comparing like the PTAC style, just pulling some fresh air, 25 CFM into a fan coil unit, that would be factored in there. But if you're looking at a full built-up DOAS system, it's not. Okay, so there's 2 questions there. There was talk a little bit about the operating and maintaining these systems, especially as they grow in scale. Is that correct? And then the second question had to do with the control system or build-in automation system related to it. I'm going to answer the first question right now. There is a section of this presentation that's going to go over VRF and build-in automation and how they play together, the different options you have available to them. So I'm going to save that for when we have the slides to support it. But maintenance-wise, any piece of mechanical equipment needs maintenance. That's anyone who says that these systems don't require maintenance is lying to you, and you're going to be upset with them in a few years after you don't do any. The beauty of these systems is that the maintenance required on them is less than conventional pieces of equipment. With a VRF system, the main things you need to do are keep filters clean, especially on these ductless units where they're not meant for high static pressure, they're not meant to push through dirty filters, is keep those filters clean. Keep the coils clean. So if you look at your outdoor units, the compressorized units that you might have on the roof or outside, make sure those are free and clear of debris, whether it's Dunkin' Donuts cups, leaves, tree sap. I mean, we've seen anything clog these coils, so they do have to be cleaned. And then you have condensate, depending on how your condensate system is with all these different fan coils, keep those free and clear. A good best practice is to have maintenance. Every manufacturer has maintenance software, maintenance tools to record system data. Is when you install it, get a baseline and we recommend annual checkups where you actually run that maintenance data again and compare that to what you had before, just to keep a track record of how the system's operating. But that's generally it. Everything on these systems are made to last the life of the equipment. There's not fan belts to replace. There's not scheduled maintenance for major components of the system. It's if you keep everything, coils clear, filters clear, the units are made to be the life of the system, which could be anywhere from, if you look at the most strict ASHRAE definition, is 15 years for any DX system. Doesn't really account for some of the pieces of equipment that VRF uses, all the way up to what manufacturers are citing is along the lines of 20 to 25 years. So that touches a little bit on the maintenance side of things. Does that answer your question? Okay, so on the question was on the complexity side. So the good news is complexity, there isn't much complexity to it. I mean, changing a filter and cleaning the filters, changing and cleaning the filter. It's not like these units need overhaul every couple of years. And as the scale goes up, your maintenance stays the same. The knock on VRF equipment is, okay, now I have, and maybe instead of one large central unit on the roof, I have 20 VRF systems on the roof. So that's 20 compressors, 20 fans, that's 20 separate modules. So yes, that is some more attention that needs to be paid because you do have more modules. And then for your specific building and how you operate, you have to consider the other side of that is, well, one, the good thing is without a central system, if one of those units have a problem, you don't lose heating and cooling in your entire building, only that section. and then it's more simplified maintenance. So I had a building we did at a university where the facility managers complained that you guys just put in over 200 ceiling cassettes throughout this building, and now we have 200 filters to change and 200 units that we have to watch after. And yes, they did have more filters to go clean, and over time they found that replacing those 200 filters or changing them, cleaning them, whatever it may be, still took less time than the annual maintenance they had to do on their conventional system that they would have used otherwise. So there might be more things to do or more units to touch and more units on there, but the complexity of what needs to be done is significantly less. The question was, do we have any data on life cycle cost comparisons between something like a 4-pipe chiller boiler system and a VRF system? Every one I've done and I've seen has always been project specific. So even if you look at just 4-pipe chiller boiler, the range of what you use for equipment can be, so you can have a one on the lower end that's okay efficiency standard system, or you can have the best-in-class chiller boiler system that's going to be pretty significantly different for life cycle costs, and that's the same with VRF. You can have a very simple heat pump system or a heat recovery with ductless units type of system. So I've seen we can help generate them on a project-specific basis. I think anyone that's printing out just a general one it's too broad. So they're out there for specific projects. Some different centers have done research studies that we can try to pull up afterwards. But I think anything that's just giving you generic technology versus technology life cycle costs is missing out on a lot of the intricacies of a unique building. So I'm going to go a little bit on the selection of a VRF system. So you've listened to this. You're convinced this is the way to go. You're convinced this is an option you at least want to consider for your building. Here are some things to think about. So buildings well suited to VRF. Any building that requires individual temperature control or zoning. So JS said it before, and I couldn't agree more. If you have a large warehouse, a box office store like a Home Depot or a Walmart, VRF is not going to make any sense. We can do it. It's just there's going to be other more cost-effective options if you just have one big giant zone with very little concern about temperature swings or how that building's zoned. Once you start getting into buildings that require zoning, office buildings, multifamily residential, all sorts of educational now, restaurants, hotels, assisted living, whatever that may be, those are all buildings where there's potential to need a high level of individual temperature control or a high level of zoning. Like JS said, if you're in a hotel, you can't be in a room and say, well, I'm too hot in here because the average of all the other people around me want to be warmer too. No, if you're paying to stay in a hotel, you want to be at that temperature you put on the thermostat, and those are the situations where VRF really starts to shine. And this is what we're seeing in all sorts of buildings, even buildings like this. Buildings are becoming very mixed use. So this is a building that has, just walking on the first floor, I don't even know it's upstairs, first floor has common space, so there's all the corridors or the atrium where we walked in. I saw a whole bunch of cubicles out by the bathroom. I saw some private offices on the other side, and then there's multifunction rooms like this, all that have different requirements. So this is the type of building that's well suited to a zoning system, because it could be the middle of winter, and we could jam this room with this amount of people or double this amount of people, and at some point in the day, we might need cooling, even though the rest of the building doesn't. There's a need for zone control there. Other reasons buildings use VRF, anything that requires high efficiency. So if you're looking at passive house, net zero, or just someone who cares about the energy efficiency of their building, VRF's a great option to consider. And then I always like to add in any building that have noise constraints. This is very quiet equipment. Every manufacturer published sound data at different sound octave levels and different scenarios. I've installed more systems than I'd like to admit, where you ask someone, why did you choose VRF? What sold you on it? And it's really just, it was the only option that allowed them to meet the sound code that they had in their specific area. Especially when you start getting in the city near Cambridge and Back Bay and all those areas. Sometimes just having very quiet equipment helps. That slide was titled New Construction. It's going to be no surprise that retrofits is really all the same stuff. Nothing changed in the top here. Once you get into retrofits, that's where you start to consider what are the benefits of having that flexible refrigerant piping. If you look at a lot of existing buildings built 40 years ago, 50 years ago, they have no existing air conditioning infrastructure that can be retrofitted. That you need to add all new equipment. It's not just, well, the ductwork's there, I'm just going to switch out this unit with one that can do heating and cooling. You're typically going into a building, usually with some architectural sensitivity, that needs to be, or it's much easier to run this flexible refrigerant piping that's very small rather than to start running ductwork where you may not have the room for it, whether it's low ceilings or not having chases in the building. That's the type of thing where VRF can really help out, is just getting into those tight spaces that require a little bit more flexibility. On the retrofit side, then there's a few more things you can look at. We've really spent all this time describing air-cooled VRF. That's where you have a unit on the roof or outside that's pulling heat from the outside air or pulling heat from the building and rejecting it outdoors. Water-cooled VRF does exist. It is fairly common. Here's a picture of a bunch of water-cooled VRF units installed in a retrofit application. Water-cooled works great when you might be doing a renovation of a building or an existing building that already has a condenser water loop. So there was water source heat pumps there from years ago. There's already a cooling tower that's in good shape. There's already that condenser water loop infrastructure there. Integrating water-cooled VRF into that is a very good option. It might even help sway your first cost a little bit by taking advantage of how that system lays out and what you already have in the building. Consider integration with existing equipment. VRF is commonly used. The heat pump systems are used quite a bit for cooling overlays. So even though they are capable of being your only source of heat, I've done plenty of schools where the school was built with heating only, and now they're looking to use the school building 365 days a year, summer programs, community events, whatever it may be. They're just overlaying cooling, integrating the controls so that it works with the existing heating system, and that's a good option for retrofits. And then it's always worth mentioning to review different efficiency opportunities in the building envelope before sizing the HVAC system. So don't just take a VRF system and say, well, there's a 300,000 BTU boiler in here before, I'm going to put a 300,000 BTU VRF system in and call it a day. With VRF systems, you really have the ability to right-size the equipment for your building. So make sure you take advantage of any low-hanging fruit so that you can right-size your VRF system and get the most efficient package rather than just the efficient piece of equipment. When looking at equipment selection, so here are some pictures of different outdoor units. Just like to give people an idea of when you're looking at a building, what do you have to keep in mind? You're going to need to locate equipment somewhere. This bottom picture is probably the most clear that shows the outdoor units. This is about 40 tons worth of equipment. This is all on a roof. This one's on a snow stand, which we recommend for anything in the Northeast. And just the reason I like to point that out is when you're looking at dimensions of this equipment, add an extra 12 to 18 inches to it because you are going to need to lift it up off the ground. The reason I like to mention that is about a year ago completed the VRF system where it was a similar situation where we were given a presentation to an architect. They loved the system, they loved the flexibility, they saw the units and how easy they were to hide somewhere. And then up here is what we ended up installing. They were expecting one of these and they got this. Well, this is a unit on snow stands with snow hail guards, with snow hoods, because they were worried about ice falling from the roof and damaging equipment like it had before this. And the email was, what is this monstrosity you put on the side of my building? If I had known about that, we would have moved them to the other side of the building. So it's just consider where these units are going, what they look like, and what accessories you might be using that are specific to your building. We are going to get going again. Perfect. I'm going to go through all the different typical indoor unit options you have with these systems and give you a little bit of information about each one. Then I'm going to pass this back to JS, who's going to go a little bit into ventilation controls. Then we'll get into our case studies. So when most people think mini splits and VRF systems, this is what comes to mind first, the wall-mounted units. This is what, when this technology came to the US, this is the majority of what was used or what was available. And there's a reason for that. That is, if you look at overseas where the adoption of this technology is 80% of the HVAC market, 85% of the HVAC market, this is the most common unit. This is the least expensive to install and the most efficient unit. So this is that, I'm sure we've all had clients before that say this needs to be the most efficient building possible. I don't have any money, so the install cost needs to be cheap. And, oh, I really care about aesthetics, so I don't want to see anything. Like everyone wants everything. But If you have a building where you care about efficiency and you want it to the lowest install cost possible, wall mount units are most likely going to be your option here. Anytime I do a presentation like this for architects, they usually want to kill me at that point because they say these look terrible and they don't want to see them, and that's a challenge. But because these aren't pushing through ductwork, these are the most efficient units that are out there. The downside to these units is that these are the one type of unit that have no way to integrate ventilation air to directly. So when JS talks about ventilation air, one of the options he's going to go over is how it can be integrated directly to the system. These types of units have no way of ducting the ventilation air to that wall mount unit. You have to introduce it directly to the space, directly near the unit, some other detached method. But this is the one downside of these is there's no way to bring that ventilation air directly to them. But wall mount units are great. We're seeing a big uptick in acceptance of them. And it's the main reason they cost the least amount of money because that's what every other part of the world uses. So they're just made in such larger quantities. Next up, we have seal and suspended units. So this is still a ductless unit, just a little bit different form factor. I see these used a lot in kitchens, classrooms, and wide open spaces, something like this. They're physically a little bit bigger. You can see it up in the corner there. Because they're bigger, they have bigger fans, and they have the ability to throw air farther. So this can throw air about 30, 35 feet down a wall. Perfect for this corner here. The windows are where you mostly have your heating and cooling load. So we're throwing air all down along those windows for an entire classroom. And the benefit here is the unit's up off the ground, and no one can touch it. So I like calling them classroom units because, one, usually it's a retrofit application, so you can install this without tearing into the ceiling, tearing into anything below the building or on the side. And then when all these kids come in, throw their backpacks somewhere, throw books somewhere, throw crayons somewhere, it's not going into something like a floor console unit. It's up out of the way and can't be touched, which is the safest place for an HVAC unit. One of the units I'm going to show next is a floor console unit, so it looks like a cabinet unit heater. And we did a school where we put all those along under the windows, which is a great place to have them, really introduce the heating and cooling right to where the load is. And in a year, we got a call for no cooling, or no heat, one of the two. And when the service tech went out to look at the units, it was a rainy day, so the students came in, threw all their backpacks on top of the units because they wanted to dry them out, and there was zero airflow into the building. Units shut off because they just weren't even getting any airflow across the coil. So that's why in school-type applications, we like units like this because it gets it so people can't touch them and let the system work as designed. Question over there. Yeah. So these units are, the primary thing with a wall mount unit is to be as small and compact as possible. So there's just no place to connect ventilation air to. Once you have a unit like this that's a little bit bigger, all these other ductless units most manufacturers give a knockout on the unit where you can introduce the ducted ventilation air directly to it. So on this unit, at the back of this unit, if we look at the direct opposite side of this on the back, there's actually a 4-inch round knockout that you can duct ventilation air into, and that will allow it to mix into the return airstream.
About outside air?
Yep, that's exactly what I'm talking about. Ventilation, fresh air, outside air, all the same stuff, yeah. One of the units, as we go through the units, I'll point out that there are some that seem to take a priority in residential. These just haven't been a popular one for residential because there's typically other options that fit the residential world better. In the residential world, wall mounts are always big for that. I have a bonus room above a garage. I need a heat and cool. That was never part of the original system. So wall mounts become popular there, and I'll point out some others as we go that are popular for that application. So these are typically more seen on the commercial side systems. They could be used for residential. It's just this might be a little more obtrusive to a homeowner when you have lower ceiling height anyway. It's kind of a difficult sell there. Another option, floor standing units. These have become more popular in both commercial and residential applications. This is actually a building here in Boston, right in the 4 Point Seaport area. And the big things the architect wanted to do was to keep this beautiful wood beam ceiling. They didn't want any ductwork in the space. And they're limited to what they could do to these windows. So their main concern was use a wall mount unit. The only wall they could put it on was on the other side of the room. But these windows were going to be drafty. These weren't high efficiency good windows. They're very limited to what they could do with them. So this now is putting the heat on a cold day right where the heat source is and is just preventing drafts. So it's a very good design there as far as how you're delivering the heat to the space. And it's fairly out of the way. These units are all stacked. And The only thing you see in the space is up on the roof, you see a refrigerant pipe go along the ceiling and jump up to where the unit is above it. So this allows you to get rid of the ductwork. There is the option to bring ventilation air into the bottom, which is the return air here. There are a few different methods that you can have the fresh air, ventilation air brought in and introduced to that unit so it's delivered to the space. Same exact as what we just shown, just uncased. It's that unit without the casing around it, so it's a little bit smaller. And these units can be built into existing millwork, around millwork, whatever it may be. This is actually a pretty common application. This is a ballroom, so you wouldn't really think of a ductless unit for a big ballroom. There's just a lot of these. They actually replaced where the radiators went. So they had radiators all along the exterior wall, and they had this fairly nice looking woodwork to hide it and allow for airflow there. So ripped out the radiators, used the piping that was left, used the chase that was left by the piping being removed to run refrigerant lines, and fit these right in the same cabinet. And between beginning and end of the project, there's no visual difference on what was happening in the space. Then we get in the ducted unit. Ducted units are probably half of what's being sold in the United States, to the point where most of the time when I deal with our headquarters in Japan, one of the biggest questions they have is, why do you guys keep buying more and more ducted units around here? It's just conventionally what we're used to in the US. There are several different types of ducted units. They're typically broken up by both size, so capacity, how much BTUs they can deliver, and then static pressure, which is how much ductwork they can handle. So a common one would be our low-profile ducted unit. Low profile, so they're under 8 inches tall, but because they're low profile, they can't handle as much ductwork on them. So they're very common for a hotel like this. Put your low-profile static unit right at the doorway, above the bathroom, whatever it may be, a couple feet of ductwork, then the air is delivered to the space. Pretty common, works very well. Then from a step up from that, you have a medium static, so a medium profile unit, which can handle significantly more ductwork, but it's also 2 inches taller. So this is kind of the standard unit that'd be used for a space like this. You can put a ducted unit right in the middle of this room, duct to all sides of the room, and there's plenty of static pressure to handle that. All the way up to your conventional larger, you can get a high static ducted unit, an 8-ton ducted unit that's serving a very large space with a lot of conventional ductwork. Not going to be your most efficient option. Again, this is back more towards the way conventional systems are designed without much zoning, but it's a possibility and fits certain scenarios. You might use something like this to do the entire atrium here in the building like this. Then on the ducted side as well, there's vertical ducted units. So these were like pancake style, horizontal ducted. Same concept with these vertical ducted unit, just specifically made to match the North American market a little bit more. So if you think the kind of built out corner in a multifamily residential unit that has your vertical stack heat pump or your vertical fan coil unit, this is a replacement for that. Similar to if you're looking at a single family home, these are basically furnished replacement type units that just fit that, give you options when you're designing it. This would go in a closet or be built out in a wall, whereas this would go in a ceiling. And it all depends on what constraints you have in the building. With all these ducted units, you're introducing fresh air, ventilation air directly into the ductwork so that that air can be introduced to the ductwork, mixed through the unit so that it's getting conditioned at the coil of the unit, and then it's distributed to the supply air ductwork that you have throughout the building. Yes? Yeah, that's a great question. The question was, are these multi-positional? Can you do them horizontal? These vertical style units, even though they're called vertical, there is a slow shift to start calling them multi-position units. So these units can be installed upflow, downflow, and then installed typically on either side as well. So just flexibility as far as where you put them. These types of units are just as good as the horizontal. It's really what fits your space. So yeah, you can put these. Sometimes people like to put these laid on their side. That's just because what they have space for and how things fit. It's all architectural as far as, okay, this is taller but skinnier. This is not as tall but wider. And it's all what fits your space. And then they all come in different configurations to make sure you get the airflow configuration you need. That's a great question. Then back to the ductless side, there's one-way cassettes. These are kind of meant to mimic linear diffusers. This is a building where here's your windows all along here, and here's your one-way cassettes all blowing towards the window all along the side hallway here. These are fairly common, especially in drop ceilings. Where they're becoming more common is this is actually becoming very common in residential applications. So the beauty of these is that they can be completely serviced from the bottom. So service access can be completely done from the bottom on these. So they're being used in residential applications where there's maybe not an attic to put the equipment where it can be serviced later, but you have to go service it, you pull this faceplate down, and you get access to everything there. All the units except for the wall-mounted unit have a condensate lift. So it's the ability to lift condensate up, usually 30 inches, then it will be gravity drained. If that doesn't fit your application, then a condensate pump can be used on any of these. So you'd use a third-party condensate pump that will collect the condensate and then pump it out of the immediate area. And then these have become popular in residential just because they're starting to be made in sizes that can fit in traditional construction as far as beam space and in those applications. A very common commercial unit, especially for office buildings, are four-way cassettes. So these are typically installed in drop ceilings mainly because the small ones do need access from the sides. The four-ways are capable of service access from the bottom. But this is return air through the center of the unit. Then there's 4 vanes that go around, that go on each side that can distribute air equally out in all 4 directions. So you can put this in a conference room like this. It goes in the center of the room, and you're getting airflow in all 4 directions towards all 4 walls. And allows you to cover a pretty large space all from one unit. Comfortably cover a pretty large space all from one unit. We already had that slide. So I'm going to bring JS back up to talk about fresh air and some insight into controls.
Okay, so we've already mentioned, again, the words fresh air, ventilation air, outside air. They all refer to the same thing. Basically, any new building now or any major retrofit needs to basically meet a certain version of the ASHRAE 62.1, which is the general standard around how much fresh air you got to bring into a building, depending on occupancy, size, and all that. So this building here also has fresh air. Majority of buildings have that. So I made a comment earlier about how do you do that. PTACs can bring in fresh air directly. There's certain systems that can, like a VAV system, a package rooftop VAV system will also handle fresh air directly and all that. So there are systems that can do it. A lot of the systems that we compare these to, like water source heat pump, chiller fan coil systems, all need a certain other method of fresh air. The word DOAS is often used, dedicated outside air unit, as a decoupled system. So essentially, here's your VRF system, or here's your water source heat pump, your ground source heat pump, chiller, fan coil, whatever it might be. Here's a separate unit that's either on the roof or indoors, depending on the design, that's going to treat your outside air, your fresh air, and deliver it to the building. ERVs are also called energy recovery ventilators. They're kind of one and the same because a DOAS unit, like this rooftop machine, it might look like just a rooftop, but it can have an energy wheel in there. The 2 main methods of energy recovery are the heat wheels and the plate heat exchangers. The wheels are great. They're very, very efficient. The only thing is it's a wheel, so it can fail. There's a motor, sometimes a belt, sometimes not. Also, a wheel will go into defrost cycles. On very cold days, it'll slow down or even stop. That's the disadvantage. A flat plate core used to be much less efficient. It's becoming a lot more efficient, much closer to a wheel. It's got no moving parts. It's got no cross-contamination, but also it has no defrost cycles. The disadvantage, it's very big. You can fit a wheel in a rooftop 6 inches of length, whereas a core may be 6 feet of length. That's how big of a difference it might be in a 10,000 CFM unit. So DOAS units, ERVs, they can be one and the same. I'll go through some different options here. What's going on in the past decade or so is a lot of the large VRF manufacturers realize, about the 3rd question I get asked when I present on VRF is, what do you do about fresh air? It's a big subject. So a lot of the VRF manufacturers started building their own, whether they build their own DOAS units, their own ERVs, or they have some sort of partnership in a way to be able to deliver the full solution for the building. Because HVAC is heating and ventilation and air conditioning, so they want to get the V in HVAC as well. So I'll go over a few options. A lot of manufacturers have a VRF ERV. We're going to get good at acronyms here today. It's a mouthful. But these are ERVs, or energy recovery ventilators, built by the VRF manufacturers. This is what it looks like over here. It's a box with a couple fans and the core in the middle, like I mentioned earlier, a little rectangular core. So the pros and cons of these, what's great about them, they're very simple, they're very cost effective, they're pretty small, and you can put them up in a ceiling and pretty easily, control-wise, they can integrate right in with the VRF controls. They can interlock with other fan coils easily or with central controllers. We'll talk about that later. The disadvantage, well, they only go up to about 1,200 CFM, so that's pretty small. And B, these guys need a little bit of preheat. They don't like just to ensure we don't have any frost on the core. the way they're designed. So you need to consider some preheat into the building, especially if your building is humidified, if your fresh air is humidified. So these are quite common. These are not your multi-res residential 80 CFM ERVs you put in each condo suite. These start at 300, so that'd be, they don't go down that small. But that is an option here. Concept is energy recovery, right? You duct your exhaust air to one of these. Could be your kitchen, could be your bathroom. Out of this, and then you preheat your outside air that way. So you take that fresh air and then you bring that to the back of a ducted unit or to a ductless unit. Greg was explaining how there's some ductless units that have connections. That's the concept here. It's got to be engineered. It's got to be thought of. You got to think about, what is my supply air temperature on a design day? Do I need to put some more heating or cooling past it? Do I bring that air directly into my space, like a picture that he's shown? Or do I bring it to the back of a fan coil so the fan coil can take care of the rest? Those are all considerations for fresh air with VRF. It's a cost, comfort, energy discussion every time. Okay, so on these ERVs, correct, there's no coil in here, just a box and a fan and a core. The blue lines show the condenser wired to the units, the thermostat wired here. Thermostat can be wired to an ERV and then daisy chain to the fan coils it serves. There's all sorts of options there. And down here, this shows the ERV ducted directly into the space. Always raise a flag when you do that, because in the middle of the winter on your 0-degree day, your discharge air on an ERV might be high 40s, low 50s. If you dump that directly into the space, that means that somebody somewhere is going to feel 55 degrees coming and they'll think the air conditioning's on, but it's not. So if you just have an ERV, it makes a lot of sense to not do like my picture, and to bring the air into a cassette or a ducted unit so that at least if it's 20%, usually fresh air rates are 10%, 20%, 25% of the airflow in the space by the unit. So a 500 CFM cassette, you put in 50 CFM of air, of fresh air. That way, even if it's 55, it's going to mix with the rest of it and you won't feel it. So those are things to take into account. If you do want to bring air directly into the space, I would look at different types of units, which we'll get into here, that can handle all heating and cooling of the fresh air. There are some fan coils you can use. So this one has refrigerant connected to it. You can use VRF fan coils that are designed to do fresh air. But when I say designed to do fresh air, what they really should say, it's designed to do fresh air in the south, not as much in the north. So what that means is a DX, DX is short for direct expansion, which means refrigeration. So a refrigerant system, which is what VRF and air source heat pumps are, isn't really designed to take air straight from 0 degrees to 70 degrees. Again, extracting the heat outside with a condenser is no problem. We talked about that, right down to 0, -4, -10, -20. But raising the temperature of air from 0 to 70 is an issue. So they have minimum entering air temperature in the 20s. So you need some preheat there. So they're very, very popular down south. Not as popular up here, but they are an option. They're very cost effective and they're very efficient, because now you do heating and cooling of your fresh air with your very efficient VRF condensing unit. The DOAS systems are very popular. This is a picture of, to the naked eye, it looks like this one of the rooftops you see on the roofs everywhere. It's not a regular rooftop. It is meant for fresh air, whether it's 100% fresh air or partly. So a couple things has happened here. You can buy a regular DOAS unit by any manufacturer and throw that onto your building, and that handles the fresh air, and it's completely independent from whatever VRF you're putting in the building. Or like I mentioned, a lot of VRF manufacturers now build their own. Some VRF manufacturers have built these with VRF inverter compressors in them, with VRF condenser fans in them. That's one way. Some VRF manufacturers have done this. So here's a rooftop, but there's no condenser section in it. You just use our condensing unit and connect it. So that happens too. So now your entire fresh air, and this can have a wheel for energy recovery if you like in there. So this condensing unit now can handle the heating and cooling, or what we call the trimming. Trimming is, I got a wheel, so on design day I'm coming out at 50 degrees. I want a coil to take it from 50 to 70. Or in the summer, I've got a wheel, so I'm taking my outside air from 95 degrees down to the high 70s. Now I'm going to put a coil to cool it to 55 and reheat it so I can do all my dehumidification. Those are all fresh air concepts that you can do depending on your application. So again, some VRF manufacturers now are getting in the business of doing those units or tying them into their condensing units, whether they build their own or they partner with a DOAS unit manufacturer and connect their condensing units to it. Any questions on that? This is the packaged version of it. Again, to the naked eye, even more, this is looks like a typical packaged DOAS unit that can do fresh air into your building. but the compressors in there are VRF compressors, VRF condenser fans. Doesn't have to be. It could be a regular unit, but it needs to be a DOAS unit. So you'll see that. Very typical. You look at a roof of a building, VRF, you got 10 VRF machines and one of those. Again, this does not handle heating and cooling, usually, if you have VRF. VRF does all heating and cooling because that's where a lot of the tonnage is, and we move that heat with little pipes throughout the building like we talked about. This is only sized in a building for the air required for the fresh air only. That's why a VAV system has big ducts. This just has small ducts because you're only bringing in 80 CFM in a room. Maybe a big room like this would be a few hundred CFM. Then there's the custom world. Again, if you're more in the HVAC industry, the more you get into applied buildings, larger buildings, you get to the custom world. So where this ties into our discussion today is that if you want to do a custom roof-mounted energy recovery unit, a custom roof-mounted air handler, a custom DOAS unit, which is a big percentage of the market, you can do that and tie any of those to a VRF condensing unit. So that will happen now. It's like, I'm doing a whole building. I have no chilled water or hot water in the building because I'm doing an all-electric building. But for this part of the building, I need a full 50,000 CFM unit for whatever reason. I need to do some cooling or some heating in it between wheels or after wheels. We can just put a VRF coil in there. So that's about a lot of the evolution with fresh air. The ERV technology I referred to earlier, there's a lot of evolution in that world. Even without wheels, there are ERVs that can do 90% sensible recovery. What that means is you bring in return air, supply air, and on a 0 degree there, you're going to get 65 degrees out of there for free, essentially free meaning for no operational cost other than the fans. So those don't even need any trimming because 65 is good enough to bring right to the space. So ERV technology is continually improving. Some manufacturers will put VRF coils inside their ERVs, again, for that trimming. So there's all sorts of evolution there. I'm going to jump into controls. I did the ventilation section relatively quickly. Is there any other questions on that I can elaborate regarding fresh air with VRF and these decoupled systems? Go ahead. Okay, this is the one. This is the one slide on controls. This could be a 1 hour or an 8 hour presentation. We're going to do it in one slide. Controls is a fantastic discussion with VRF because if you bought a VRF system, you basically bought a control system. What that means is any VRF system that you install, for it to turn on, that condensing unit is going to be wired to all the fan coils, all the indoor units, and you're going to use our thermostats. You can use my thermostats in my system. You can use Greg's thermostat with his systems because a regular thermostat just doesn't have the intelligence to tell us what we need to run our systems. Even a Nest thermostat is too basic. A Nest is smart at figuring out what you're doing, but the output of a Nest thermostat or the output of a regular thermostat just says, click, I want cooling, or click, I want heating. Some of them have fan speed. Click high speed, click low speed. Even the output of a Nest is the same thing. It intelligently does that, but that's all it has. For us, our fan coil is like, whoa, I don't want to know if you're just cooling. How much cooling do you want? So that's why you got to use the VRF thermostats because they send the room temperature that's exactly at every second. It's not every second, but it's going to send the set point all the time, and our control board is going to take in all this information and then figure out what to do. So there are ways of using regular thermostats, and it really dumbs down our system, and it turns our system into kind of an on-off regular. All we know is you want cooling? Okay, I'm just going to turn on and go full blast. It doesn't take advantage of the variable capacity of the systems. So if you bought a VRF system, you bought a control system in that you're using our thermostats, and our condenser is the motherboard and sees what's going on. If you leave it like that, you haven't yet brought in any sort of way to remote into the system remotely and all that. What's neat, though, is if you want to do that, if you want any sort of central control, there's sort of two paths you can take. Path one is going to be, hey, I'm on a big school campus, and they have brand A, B, C, D, or E of major controls company out there on campus, and they want to see your system through there. No problem. Usually we're going to include a central backnet interface. All VRF backnet, at least commercial VRF, is going to be over IP just because the amount of data that goes through it. MSTP would be a little limiting. So usually it's over IP. That's how we would do it. And there's a whole conversation about how to integrate BAS systems into VRF or VRF into BAS systems. The good news is if you had a water source heat pump job with 100 water source heat pumps in this building and you said, okay, I want to integrate those with BAS, a controls company would come in and say, okay, I got to buy a little board and I got to go put it on each of those water source heat pumps. Then I have to wire them back to my field controllers and back to and then give you some sort of graphic. With VRF, if somebody says, I got 100 units in this building with VRF, since I want to control those, all we have to do is take our condensing units, because our motherboards there are already wired to all the units, and daisy chain those to a central controller with the BACnet license on there. So that's option one. Big BAS, big building. I want to integrate JCI, Siemens, Honeywell, Distech, whatever company it might be. You can integrate with them that way. The other option, and that's usually the big part of the story with VRF controls, is because you already bought a control system, the VRF now are saying, hey, if you don't need or want one of the big controls on the job, think of it as a 100,000 square feet or less building, independent school building, whatever it might be, you can use a VRF central controller. So now the VRF people have built their own little touchscreen over there that it's a plug and play central controller. You put that on the wall, you wire it to the condensing units, and you're done. From there, you automatically, without demanding graphics, without hiring a controls company, you can see and touch all the VRF indoor units, set points, scheduling, room temperatures. You bring internet to it, just an Ethernet cord to bring internet. Now you can remote in from anywhere, automatic alerts. You can have your service person emailed, error code F3 on classroom 203. Goes online, checks it. Oh, I have a condensate pump that's is giving me an error. Float switch tripped in classroom 201. Right, that's the kind of stuff you can do without having a full control system or a full controls company, just through this central controller. So that's not new. That existed 10 years ago, 20 years ago. What's evolved in the past 5 years, I would say, is somebody will say, okay, that's great, Mr. VRF manufacturer. I can see and touch and play with all your fan coils, but I don't have just VRF on the job. I got that DOAS unit we talked about. I've also got some exhaust fans doing some stuff. I got other things in there. How do I do that? So I got to hire somebody anyways to come in and do controls for that. So now the idea is these units have all sorts of ways of integrating third-party equipment. They can be done through just the, analog connections, digital connections, or even through BACnet. So what that means now is this system can talk to the DOAS units. Of course, if you're using a VRF manufacturer's DOAS, it talks the same language and goes right in. But if it's a third-party DOAS unit, we can use all sorts of different connectors to be able to talk to those. So what that means now is on your manufacturer A's central controller, you see all the VRF units, and then you're going to see manufacturer E's rooftop unit, manufacturer F's exhaust fan, if ever you decided to mix and match or you're going into an older building. That's a big part of the story now. Again, if I'm going into, let's just say where I was yesterday, I'm going into Harvard to install a VRF job. I'm not even talking about, hey, you don't need it. I'm going to get thrown out. They're going to say, no, you're going to integrate with this manufacturer. Here's my BACnet card, away you go. But there's a lot of applications where for a very low cost, relative to the cost of the project, you can have a pre-packaged central controller. A couple key things about the central controller. One of them is energy distribution. It's a very, very big topic in the world of VRF, especially when we're trying to do multi-residential buildings with VRF. Why? What's the difference in a building that has 100 multi-splits or 100 single splits for 100 suites and going with VRF? What's the biggest hurdle in doing that? What's the big difference between 100 single splits and doing 10 VRF condensers on the roof each serving 10 suites? Metering, exactly. Who pays the bill? If you have a single split, that on the balcony, that condensing on the roof is going to be wired to the panel in the suite right there, and that panel is already sub-metered by NatGrid or by National Grid or Eversource or whoever you might have. Now I've got one machine on the roof serving 10 suites. Who pays for what? In my mind, I think that's been one of the biggest hurdles, especially in states like Massachusetts, to do that. I'll explain why. So VRF manufacturers with this controller have the technology, factory mounted basically, to be able to distribute and attribute the energy use. Remember the expansion valve we talked about inside that fan coil that's got 2,000 position that gets monitored? That in its own is a metering device. And because the condensers know what all the metering devices are doing, and because we're tying it to central controller, this central controller at any point in time knows exactly what each metering device, all 100 of them in the building, are doing. So what it can do with an energy distribution software is if you plug in some power meters so you can calculate how much electricity the central units are doing, and you wire that and tell that to the central controller, it'll distribute that for you. It'll run an algorithm every 20 seconds to figure out where all the expansion valves are, and it'll say, okay, in the past hour, condenser unit A, you used 10 kilowatt hours. I'm making up numbers. Fan coil A, you're responsible for 1.2 kilowatt hours. Fan coil B, you're responsible for 1.6. Fan coil C, 0.8. Fan coil D, and so on and so forth. So the manufacturers go as far as giving you this data that you can extract from the central controller, and from there, an owner or a building company can use that to distribute the cost of the HVAC. Very common in New York City, common in Rhode Island, common in New Hampshire. Massachusetts, we're getting there. We're doing more and more jobs. The way that the law is written around the resale of electricity, some owners are concerned about that. Well, am I going to get in trouble for reselling? Well, no, you're reselling HVAC, not electricity. So some owners are doing it. Some owners are not. That's where the challenge is. But the technology is there. You need a central controller because that's where the algorithm lives. You need power meters to meter the condensing units. If you have 10 condensing units, you need 10 power meters. Unless you put all 10 condensing units in one dedicated electric panel and nothing else on it, then you can use 1 meter for the entire panel and bring it into the central controller. That's energy distribution or attribution. Peak load shedding options. Those are some options, some terminals you can use. Let's say you got a generator and you want to limit how much energy the condenser can use during a generator period. If you are going to put the VRF on backup generator, time of use electricity, you want to not, in certain periods, you want to be able to say, let me slow down or limit my condenser use because I'm getting charged peak load right now. Those are options here as well. That is my only slide on controls. I'd like to open it up and open up for questions on controls. Go ahead. That's a good question. The question is, how does energy distribution work with heat recovery? So what I'm going to do is I'm going to compare it to how people do tenant metering or tenant billing with water source heat pumps. Usually water source heat pumps, what happens is it's great because that heat pump in the suite, that vertical stack heat pump, is powered by the suite owner. So that owner pays for that compressor that's running. What the house pays for is in the middle of summer, the cooling tower or the boiler. What happens in the water source heat pump is if you're in the middle of summer and you use your unit a lot, you're cooling a bunch, you're going to pay more. You're running the compressor more. What happens in the middle of the winter is, let's say everybody's in heating mode. Everybody's heating, but you're having a party. So you run your heat pump in cooling. You're actually helping everybody else because you're taking heat from your condo and putting it in the water, which everybody's using because they're not having a party and they need some heat, right? So there, in the water source heat pump, that cannot be taken advantage of. You're still going to pay for that electricity for that water source heat pump. The same thing happens a bit in heat recovery. So if you're in the middle of the winter and everybody is in heating mode on a VRF system, and you over here are using cooling, right? In theory, you're helping everybody else a little bit. You're taking the entire energy use compared to if you were doing heating, and you're taking it down a little bit. But you're still going to pay for your use of it. So the technology is not there yet to be able to say, hold on now, you've kind of helped the entire efficiency of the system because you're off-season using a different mode. You're in the summer heating for some reason. That's less common. You're in the winter and you're cooling. The technology is not there yet. So it's similar to the way people do metering and water source heat pumps or other systems. So it's not worse than alternatives, but it's not better yet. So you'll still win if everybody's using, it's a perfect setup. I got half heating, half cooling. Overall, the energy use is going to go down. That meter that measures the condensing unit power is going to show 8 kilowatts instead of 10 for that last hour, kilowatt hours, right? So that's great. So everybody pays less, but they all pay the same percentage. Long story short, if I use 2 BTUs in the past hour, whether I use them for cooling or heating, I still get charged the same. But if I use it for cooling in the middle of the winter, the overall use will go down because of the heat recovery. So it works. It just doesn't take advantage of those weird, funky off-season periods where we could. Fair enough. Any other questions? Go ahead. So it all depends on what you are doing on the building side. For us on the VRF side, all we have is a terminal. The terminal that says you close that contact, and I'm going to maximize my use to 40% or 50% or 60%. What you use to enable that contact is up to you. Whether you just want to do it manually, whether you got something that's tied into the time of use electricity by the grid, whether your generator output, whatever it might be. What we provide is that contact that says you can tell me if you want me to peak to shed on peak or to limit my energy use. Yeah, it's all in the software, correct. And then so if you do enable that contact for peak shedding or for load shedding in our software, it's going to tell that condensing unit, hey, if you're only asking for 20% load, you're good to go. But if ever that building starts to ask for 100%, you can't go past 40. That's what it does. So the compressor just won't go past that digitally. That's all internal. That's all done prepackaged by the VRF. You buy that board and you close that contact. We can program. I can program the percentage. So that's the people that commission the system, whether it's us as the reps or a contractor that does his own commissioning. You do have to program but it's just a contact, and then from there, it's all done internally. So the question is, the peak shedding is not done on a amp draw. So no, that's a good question. With the peak shedding, it's a percentage of use. What doesn't exist, you could program it externally. What doesn't exist is, here's an amp meter, and when I close this contact, that meter can't go past 18 amps, for example, which would be useful for generators and all that. So you have to program around that a little bit. Okay, I'm going to go to 40% or 50, so it doesn't use amp draw. It does it as a percentage load, the percentage compressor run. You should have to back calculate that to amp. Does it have peak shaving capabilities? Now, depends what you mean. If you're referring to the earlier thing I said, where when we're at peak demand, we want to allow the building to slide a little bit so that we can be more efficient. Yes, that's all in the cruise control programming I referred to earlier. If you're referring to limiting how much electricity you allow that condenser to pull during peak load, whether by peak you mean when your electrical provider is charging you more electricity, or whether you mean based on outside air temperature and all that, that uses the contacts. Something else is going to tell us when we want you to shave some use. Yeah, so the question is, can we limit the expansion valve? So it doesn't do that. It does it in a reverse way. So let me explain that. So we don't limit the expansion valve. We limit the compressor. So then in turn, it'll go and limit the expansion valve. So let's say everybody wants 100%. Everybody wants expansion valves fully open, but we've clocked this contact and the compressor is limited to 50%. In theory, it's going to go out and tell every expansion valve to close to 50%. Of course, it's never like that, because when somebody wants 30%, somebody wants 80, somebody wants 70, it'll just proportionally reduce all the fan coils is what it's going to do. Correct. That's the peak shedding. You said a limit of use. Correct. At the compressor. At the condensing unit itself, but essentially it's the compressor. Any other questions on the control side? I'm going to invite, who's first? Is it Kyle? I'm going to invite Kyle to come up and talk about the grant incentive programs.
All right, good morning, everyone. I'm Kyle Kumis. I'm with Energy Solutions. We represent the MassCEC programs, which are sponsored by, looks like it'll be on the next slide, but the different utility and program administrators. A little bit of background about the programs that I'll talk about. They all come from a little charge on your bill that everybody pays a little bit more into towards energy efficiency. And the reasoning for that and these funds are we want to lower our demand so that we can put off having to invest in infrastructure. So just using random numbers here, we'll invest $200 million in lowering our demand so that we can put off having to invest in $1 billion in a new power plant. So you guys might be familiar on the residential side of things where there are mail-in forms where you can receive a rebate. On the commercial side of things, there are also incentives available, but it's through what's known as the upstream program. And through this model, your distributor of the equipment actually processes the rebate for you. They take care of all the paperwork and pass that incentive along to the contractor, who then passes it along to the customer. In terms of what is eligible for an incentive, there are incentives for VRF equipment as well as ductless mini-split equipment. There are certain efficiency levels that the equipment must meet. That is all outlined here in terms of the EER, the part load, and as well as the heating efficiency. And then depending on how efficient the equipment is, there's extra incentives for more efficient equipment, which is based off of the part load efficiencies. And we have these tables are available, but if anybody's interested in seeing specific model numbers and what an incentive is received for that specific model, we can provide that as well. The contact information is down at the bottom. If you have questions, we can provide that to you. So that's verifying that the equipment is eligible. Next, verifying that the customer is eligible. So this is for commercial and industrial customers. It is available in Massachusetts as well as Rhode Island. And it's available for any commercial and industrial customer. When we talk commercial and industrial, how we define that is based off the meter at the site. The customer has to pay into a commercial rate, a commercial or industrial rate. So, you know, your typical schools, hospitals, restaurants, that kind of thing. Multifamily is kind of a gray area. I've seen it sometimes that it is metered commercially, sometimes that it is metered residentially. In scenarios like that, what we do is ask whether you're the customer or the contractor, designer, contact your distributor and they'll reach out to us and we can look into the site. We have all of the meters, all the utility data to check on the particular site and see if it is metered residentially or commercially and whether it will be eligible for an incentive or not. There's a pre-approval threshold as well. So with a lot of VRF systems, you're going to go over these thresholds that are 5 units or $4,000 total in incentives. What's needed there, again, is similar to what I just described, where the distributor would reach out to us with the site address and the number of units going in, and then we would provide them with an email explaining that the site is eligible for the incentives here. One really important thing to point out is for the upstream incentive, you can receive the upstream incentive as well as the incentives offered through the MassCEC and couple them together, which is great. I mentioned the program is available in Massachusetts and Rhode Island for commercial and industrial customers. That is eligible for local towns or cities that are providing their own electricity municipalities. So those are included in this as well. And I guess one other thing that wasn't on the slide that is new, come May 1st and going through June 30th, there will be an incentive for contractors. If they make a sale that qualifies for the upstream program, they'll receive a $200 incentive from the program. So the upstream program is one of many programs that are offered through MassSave, but a project can only be incentivized once. So this goes into other ways in which customers can receive incentives for certain projects, and that would be through a new construction or a major renovation program where the building owner is working directly with their MassSave program sponsor, and they can reach out directly to them and receive an incentive that doesn't involve the distributor or the contractor passing it along. What we're doing basically when the pre-approval is happening is we're checking to make sure that the customer is not already working with the utility before the distributor can pass the incentive along to the contractor. Again, this program can be coupled with the incentives from the MassCEC program. However, you cannot receive this new construction major renovation incentive as well as an upstream incentive. And it's not mentioned here, but you know, we're talking about VRF and mini multi-splits. There are incentives on other types of equipment through the upstream program and the new construction program. On the upstream side of things, the incentives are a lot higher on the VRF and mini and multi-split systems. So that's pretty much it. Are there any questions? Yes, so Energy Solutions, the company I work for, we do implement the program. So we work with distributors mostly who are offering, but if customers reach out or contractors reach out, we work with them directly to facilitate how they would go through and receive the incentive. And there's some flyers out back that go into a lot of what I just covered that you can take with you, and includes the incentive amounts listed there. The question was, we're in Boston, but are we in Springfield and? Yep, so it's available all throughout the state of Massachusetts. Springfield, Pittsfield included in that as well. And Rhode Island, if anybody is working there.
There's also an incentive program in the state that is a production incentive that is based on how much heating output your system produces over its operating life. And that is a program called the Alternative Energy Portfolio Standard. It's run by the Mass Department of Energy Resources. So basically, you as the owner of a VRF system would apply to qualify for this program, and then you would become a qualified renewable thermal generation unit. And for every 1 megawatt hour equivalent of heat that your system produces, you would also be generating something called an Alternative Energy Certificate, or AIC for short. And these AICs have a market value because the electricity suppliers in the state are required to purchase a certain number of these AICs every year to match a percentage of the electricity load that they're serving. So that creates the market for these certificates. And DOER has designed the program such that the value of the certificates are worth about $15 to $20 each. And again, this is for each megawatt hour equivalent. Systems that are installed in buildings that are qualified as zero energy or passive house or have a HERS rating of less than or equal to 50 can earn these AICs at a faster rate, but it's still proportionate to the amount of heat energy that they produce over their lifetime. So that's all very abstract. You probably want to know how much this is worth in dollars. Excuse me, there's some details available on DOER's website about this program at that link. So here are some examples of how much this might be worth for different size systems. The first row of the table shows a system that is putting out 250 MMBTUs over the course of a year. That system would generate 219 RECs. If you assume AECs, AECs. If you assume the value of each certificate is $16, then this is going to be worth about $3,500 per year. You might ask how large a building or how large a system would be putting out 250 MMBTUs over the course of the year. A very rough estimate because there's a lot of factors involved, but that might be, say, a 5,000 square foot building. So that building their system would get $3,500 a year. If that system were installed in a certified passive house building, it would be earning the AICs at a faster rate, and it would get 366 per year for over $5,800 in AIC value per year. We give an example of a larger system, maybe a 10,000 square foot building producing 500 MMBTUs per year. So it goes up, the dollar value goes up proportionately. There are some expenses related to the aggregation and verification of the AICs and getting them sold into the market. So that'll probably nick about 5 to 7% off the totals presented above. The certificates are minted every quarter, and your aggregator would probably sell them every quarter, so you'd probably get about a quarter of the value 4 times a year. So this is an ongoing program of the Department of Energy Resources. They'd like to see a lot more participation in it. That's something to be aware of. And that's all we have on incentives. Do you have any questions about either MassCEC's program or the APS? Yes. So the question was, how long can the system earn AICs, and is there a market floor price? To the best of my knowledge, there is no limit on the number of years for these commercial scale systems. You may be aware that mini splits can earn 10 years worth of AICs up front. That's only for mini splits. That doesn't apply to these commercial scale systems. But these don't get all the money up front. You get it every year or every quarter spread out. But as I understand it, there's no time limit. Your second question was, I'm sorry? Is there a floor price? That is a question I would have to defer to Department of Energy Resources to answer, but I know that they are designing this program so that the AIC price is expected to be within $15 to $20 per megawatt hour equivalent. That's the best I can tell you. I can give you a contact at DOER if you want to ask them more about that. Yeah. It is my understanding that there isn't a limit, but I'm not with the Department of Energy Resources, so I would have you confirm that with them.
So keep the questions coming. As soon as they stop, we'll move on to some case studies. If you have to leave, we won't be offended. But we'll start with a question in the back there.
The question is about refrigerants and the different phase outs that's going on. There was a big phase out of R22, and that took 25 years, I think, from day one till the day that you can no longer buy the refrigerant. You know, the phase out go in steps, and you can't produce new equipment with it. You can't use it to replace equipment. You can't replace refrigerant. It's all steps, right? So that's already been done. There was R22 VRF, a long time ago, 20 years ago, 15 years ago even. Now we're all on R410A. So R410A is already it's got zero ozone depletion potential. We've already took care of that. Now it's a global warming potential. So R410A is at around 2,000. So it's not incredibly high. It's better than the old ones, but it's still up there. So yes, there's all sorts of research, especially for chillers, right? A lot of refrigerants are coming out to be lower ozone depletion. Right now, R410A does have a phase out in certain chillers. There is no R410A phase outs for this equipment, for splits, multi-splits, residential, or VRF, which means even if tomorrow morning they announce the phase out on R410A, you would get presumably 15 to 20 years before you can no longer use that refrigerant. So that's one thing. So you're safe in terms of buying equipment today. Now, the research for next refrigerants is all over the place. Every VRF person's working on it. You go to Japan today, you go buy a mini split in Japan, it's going to use R32, which is one of the options for the next refrigerant in VRF. R32 is half of the mixture of R410A. It's very similar. It's presumably going to be a drop-in refrigerant in the future. We can't use it yet here because it's an A2 refrigerant, not an A1, until we get, if you're familiar with actually 34, until the A2L category, the new one for these refrigerants, get adopted. We're not there yet. So presumably in 10 years, possibly, you're going to see VRF here with R32 or other HFOs now or other refrigerants that are lower global warming potential. R32 is one example. That's one of them. There's other options. But you're safe today for the next, because phase outs take a very long time.
And the only thing I want to add to that JS touched on is a lot of conventional HVAC manufacturers are going around talking about refrigerant phase out. The point is that right now, R410A is only being phased out on air-cooled chillers, mainly because all the refrigerant lives outside, and they can have a flammable refrigerant. They can have a toxic refrigerant as a replacement because it's not going in the occupied space like this type of DX system is. So the phase-out that you're hearing about is not applying to VRF right now. But as JS said, every manufacturer is looking into what's next. I can think of just in our testing laboratories, we're testing 3 different types of refrigerant right now. And it's basically we want to have the data and the know-how because a lot of it's going to be based on codes. A lot of it we're not going to have a say in. We're just going to have to make sure that we can react to it appropriately. Overseas, we have R32, we have CO2, we have systems that are actually acting like air-cooled chiller where it moves all the refrigerant outside of the building and then transfers to water within the building. So it's on the radar of every manufacturer. I would say even if 10 years from now a different refrigerant is named, that's going to be a 20-year phase-out process. So not only is the equipment you buy now safe, likely your next generation equipment's also safe before you're dealing with a true phase-out of the refrigerant. It's not like they can't just end it. They can't announce next week R410A is done and then it's over. It's going to be a several decade-long transfer.
The air-cooled chillers is 2025, I believe. So you can still buy a chiller with R410A air-cooled until then, but you can still replace it with a refrigerant down the road. That's why we say 20 years, that you can't buy the refrigerant anymore. You can still buy R22 today, not for much longer, but to go replace old systems. So the question is, with refrigerants, do you see any drawbacks with leaks? So that opens up the whole subject of refrigerant leaks, risks, consequences, and all that. So the first thing is, the good news is R410A is an inert, non-toxic gas, so you could breathe it in, there's no problem. So it's safe on that front. It's not toxic, not flammable. The risk is, if you were to put a lot of refrigerant, if you were to put 5,000 pounds of refrigerant in this room, well, the refrigerant would displace the rest of the oxygen, and then we get in trouble. So that's why the ASHRAE 15 code talks about how big can your VRF system be, depending on how small the rooms are. The good news is a VRF system runs 50 pounds of refrigerant, maybe 100 for a large one, whereas a chiller it could be 10 times that, 5 times, 10 times that. But we still have to watch out. If you have a little 80 square foot offices and all that, you have to watch for that, for the life safety aspect of it. Again, it's not toxic, but if there's a lot of it, you got to be careful. So for large VRF systems, you just got to watch that. Now, the code's very conservative. It assumes a sealed space. It assumes no fresh air. That doesn't exist anymore. So that's one aspect. The other aspect is, one of the things I answer when somebody asks, what if there's a leak? Well, what doesn't happen is a bunch of water damage. Because if the refrigerant leaks, it leaks as a gas. So that's good because it doesn't damage your building. The bad news is it's harder to find, right? So they're rare because you're using refrigerant copper. The pressure tests are at 550 psi, not 300 like a water source heat pump system. So they're less common than water leaks, but they're a little harder to find. You got to do some testing. Once you find it, you got to fix it, take your system down, and all that stuff. I'll let you address it.
The only thing I add to that on that last point is, so refrigerant leaks can be easily avoided. Refrigerant systems are one of those, if you start it with no leaks, so if you install it correctly, it's very unlikely for a leak to develop. It's going to take a pretty catastrophic event in the building to develop a leak. Typically, if there's a leak, it was there from the beginning, and it was just a less than optimal installation. So one part we kind of skipped here was things you should be asking is, I see this all the time where building owners will come to me and say, well, here's this well-known mechanical contractor that can point to 20 VRF systems they've installed with references, and they're 10% more than this guy who has no record of training, never heard of him before, and they're eager to start the job. And you're going to spend a lot more than 10% of the job cost off that savings to go back and fix refrigerant leaks, because that's one of the differentiators between a contractor who's trained in the equipment, trained in the proper installation, and then testing procedures to make sure that system's tight and leak-free and clean. So it's one of those, getting it right at the beginning is infinitely better than trying to fix it after the fact. So that's really where qualifying who's doing the work for you pays off in dividends. We'll jump into some case studies. A lot of this was covered in the questions before we get there, just to finish up the presentation. Anytime you're thinking of using this technology in your projects, it's with the designer, the contractor, with anyone, is find someone who has used it before, has gone to training on it. Every manufacturers offer extensive training on design, applications, installation, and we offer that for a reason. So just make sure anyone you're choosing to work with has gotten trained on the equipment, knows what they're doing with the design, knows what they're doing with the installation. That is going to make a significant difference. And the best area to find those are manufacturers and manufacturers representatives, like those of us in this room, do lunch and learns, have sales engineers that work on this, have resources. Manufacturer's website usually lists who has completed training, so who's gone through the training course, and that's a good place to start. And then third-party groups such as even MassCEC has a designer and installer list right on their website, is a good resource as well. Case study-wise, Jason and I are each going to do one. And we each chose a project that kind of applies to something unique that was talked about today. This building I chose is a alumni center at Clark University in Worcester. Not a particularly large building. It's 35,000 square feet. But I like it as an example because not only is it's out in Worcester where it gets fairly cold. Seeing negative 10 degrees there is not all that uncommon. It's 100% heated and cooled by air source VRF. And it has been for the past 3 years now. It's a mix of office space, meeting space, event space, TA office, student conference rooms. It's a complete mix of what the building's used for. And it was finally completed in 2016, so we did get it for the previous winter of that. So I guess we're going on, 3.5 years of the building operating. So this is using a simultaneous heating and cooling cold climate VRF system. So this is a system that's made for these cold temperatures. It utilizes a refrigerant to water heat exchanger. So there is a portion of the building where they needed to use radiant floor, mainly due to a large glass exposure in a cafeteria area. So used a refrigerant to water heat exchanger off of the VRF system to provide hot water for that radiant floor. And then it used a full building automation system, or completed the task of a full building automation system by the VRF controls. So a lot of interesting things as far as electrification. There's a need for hot water, and the VRF system was able to provide that hot water for them. And then there's a need for significant amounts of heat due to the cold climate. And again, JS mentioned it before that -10 degrees might be cold to you and I, but all that means is we need refrigerant that's colder than -10 degrees, and then we can pull heat from the outside air. It's not that cold for this equipment. So some of the challenges with this project, they required a lot of future flexibility. They had a good idea of their floor plan and what they wanted different offices for, but they wanted the ability to have a system that could be renovated down the line, maybe even as soon as 5 years, to change the use of the building. They're just forward-looking. They wanted a flexible building that, as the needs of the university changed, they could change what it was being used for. It was mixed-use space, so anything from a not permanently, but a continuously occupied office to mini conference rooms that are used once a week to a cafeteria and large conference room that people are in and out of all day. They did have very lofty sustainability goals. Their end goal was net zero for this building. The building itself doesn't accomplish that, but I know paired with some future solar, it will be able to. And then they had concerns about extreme weather, cold climate. This was built right in the time of that. If you were in Massachusetts a few years ago when there was that foot of snow every Monday for a year, it felt like, or the polar vortexes. So a lot of focus was on different accessories to make sure this air source equipment could handle that comfortably. Here's a floor layout. You'll notice a lot of small offices, each one with its own fan coil and its own thermostat. So a lot of controllability because this was the dean was in every single day. These were just flex offices that could be occupied for 1 hour a day, then won't be occupied again for the rest of the week. Or it could be someone's in and out for meetings all day, presents some challenges with system design and efficiency. So one of the unique things done here was, first, they compared the air source VRF to geothermal heat pumps, mostly by doing an eQuest energy study on the entire project. One of the really cool things with this was it was monitored after the fact for, at the time it was a national grid incentive that they were going for, that had to compare actual performance to modeled performance. And it was within a few percent of the modeled performance. So the person who did the energy model was very happy with that their predicted energy use and what actual energy use was very close, much closer than expected. It was like a couple percent. Some of the ways we accomplished that were beyond the efficiency of just the VRF system itself, using some advanced controls that can really come built in with these systems for energy saving measures. First being a ventilation damper that's tied directly to the fan coil unit. So the unit's running and on because the room is occupied. That damper opens and allows ventilation air directly to the unit. Someone leaves the room and the room's unoccupied, close the damper so we're not bringing ventilation air. Why ventilate a room that doesn't need to be? Thermostat on this unit, built-in occupancy sensor. So this is what's telling that damper whether or not it should be open and whether or not the unit should run. You leave the room, 10 minutes later, the unit's being set back because it's not occupied, and it's not being turned back on until someone walks in the room. So the ability to handle a change in schedule and get that savings from not ventilating the room, not cooling or heating the room when it doesn't need to be. Then on top of that was window switches. So window switches, and these all tie directly into the fan coil. So you open the window, ventilation damper closes, and the unit shuts off. And there were alarms and safeties built in, so if it got below 50 degrees, it would alert the facility manager that a window's open so they could handle it. And something that's not shown here, but you'll notice in this building, so on your way out, take a look, and you'll notice there's red and green lights, and right now the red lights are lit up. strategy this building's using is you'll notice that all the windows are electronically operated. You don't even have the option to control them yourself. So when the conditions are right for free cooling, these windows will automatically open. And you can see the, nope, I'm talking about there's one right in the kitchen, and you'll see them more prominent in the lobby. It's an actual silver plate on the wall right near a light switch that has a red and a green light. So a green light means the conditions are there for free cool and the window's open. We took a similar method with this, except we didn't automate the windows. All we did was we're monitoring the conditions, and we alert the end user with a green light when it's beneficial to open their window. So they still have to do it themselves. It gives them the option, but it tells them it'd be wise to open the window now and get free cooling. So they go and open the window, cooling shut off at the fan coil, and ventilation shut off at the fan coil. So all stuff that's fairly easy to do with the equipment that's built into the VRF system. They applied for a few different incentives and grants to build a building like this. And part of that required trends at 1 hour intervals to confirm that the system was performing as designed. And this pulled in watt hour meters. This pulled in a lot of different data points in the system so that they could go back and look at it for a year at 15-minute intervals and find out, did the system do what the pre-designed energy model said it would? And here's just an example of this was an advanced graphics package was added on top of it to show different, this is the actual floor plan. This showed different room temperatures and allows, their basic request was a facility manager can look at this in the morning and say, okay, everything's good. This is red because it's outside our stated range. What's going on in that room? Do we care? Is something wrong? So it's just kind of made for a little bit easier maintenance. And that's a quick overview of that. Again, happy to talk about it after with anyone, but I want to make sure JS has some time to get through his case study as well.
Thank you. I'll go through this quickly, and I can always take questions at the end here. This is a job up in Lowell. You might recognize that tower at the top. If you've been up there, that's a Christmas tree in the winter. So this project is a little different. I'm going to fast forward. It's an old mill building, existing office building with all sorts of different tenants in there. And they wanted to do a retrofit. They had old 10-ton through-the-wall units. So this is a special VRF system in that there are no regular VRF fan coils in here. So I'm going to skip to the pictures because it'll keep it much quicker and simpler. So, okay, so here's the floor plan. They had a little mechanical room with 3 big 10-ton machines with all this duct work going out. And we did all this retrofit work without disturbing any of the tenants. All we did is we ripped out these units and replaced them with 3 12-ton or 10-ton VRF air handlers. So what that means is these days, one of the big developments is if the regular fan coils that Greg talked about don't work, you can build semi-custom VRF air handlers. So here that was the idea. You still get the advantage of the VRF heating and cooling, energy efficiency, comfort, and all that. We just didn't go in and put fan coils everywhere because they didn't want to zone it. They wanted to keep it the same way. So now what you're looking at here, that's a 12-ton VRF air handler. So it's a 2-piece air handler, so we could fit through doors like a regular semi-custom air handler. Fit through doors, we stacked one, stacked the other. This is your VRV expansion valve, like I talked about in the fan coils, but it's a loose one that we can install. Your expansion valve controller, that's a VFD for the supply fan that sits back there. Down here are your refrigerant lines up to the roof, and these are all the other refrigerant lines because there's 6 mechanical rooms on top of each other, each with 3 of these machines. So something to think about for retrofit work. If the idea of putting fan coils everywhere doesn't work, we can replace and reuse existing duct work here with this concept. Very cost effective. The alternative was they're going to do a water source heat pump. So big 10-ton water source heat pumps up to the roof. The problem is they could not have turned that on until everything was finished and the condenser water loop was finished. We were able to do this by doing 1 mechanical room at a time and only have 1 week of downtime per tenant and everything. So it was that was the big part of the project. Here's another picture. We even reused the existing stands from the old unit that was there. So that's a VRF unit, which means it's fed by a VRF condensing unit. So you get all the advantages of heating and cooling and efficiencies that we talked about. And we electrified the entire building. This used to have a big gas-fired unit heater in the ductwork, so that's all gone. Here's on the roof. You can use snow stands, like Greg mentioned. For a lot of units, it's often more cost-effective to put these sleepers. And also, usually vibration is not an issue because the machines are internally isolated. However, we're right above an old structure, right above the tenant space. So we actually put springs inside of these sleepers for additional isolation of sound and vibration. There's a picture of us lifting units. I always love to do those, and that's the final picture. So I'll leave it there just because we're already way over time. Any questions on that? A little bit of a different project. One thing too is we've done projects too where we kept existing air handlers. Chilled water plant was gone. We ripped out the chilled water coils. And we put in VRV coils. That's an option, or VRF coils. That's an option as well. Okay, I'll leave it as that. Any final questions for Greg or myself?